Multiverse Theory. The multiverse theory proposes that what we perceive as the universe, our vast cosmos with its galaxies, stars, planets, and physical laws, might be only one of countless other universes, each potentially governed by different physical constants, dimensions, or even fundamental laws of nature. At its essence, the theory challenges the notion of a singular, unique cosmos, suggesting instead an immense, possibly infinite collection of universes collectively referred to as the multiverse. This idea arises from both philosophical reasoning and mathematical implications of modern physics, though it remains highly controversial because of its speculative nature and the difficulty, perhaps impossibility, of direct empirical verification. The origins of the multiverse concept can be traced to attempts to explain certain puzzles in cosmology and fundamental physics. One of these puzzles involves the apparent fine-tuning of physical constants in our universe. For example, the strength of the gravitational force, the charge of the electron, and the ratio of matter to antimatter all fall within extraordinarily narrow ranges that allow for the formation of stars, galaxies, and life. If these constants had been even slightly different, the universe as we know it would not exist. This improbable coincidence raises the question of why the universe is so finely tuned for complexity. The multiverse offers a possible answer. If there exists an enormous number of universes, each with different properties, then it is not surprising that at least one of them, ours, happens to have the right conditions for life. In this view, what appears to be design is instead the result of a vast cosmic lottery. One of the strongest theoretical motivations for the multiverse arises from the concept of cosmic inflation, an extension of the Big Bang model. Inflation proposes that the universe underwent an extremely rapid expansion in the first fraction of a second after the Big Bang, smoothing out irregularities and explaining the large-scale uniformity of the cosmos. However, some models of inflation suggest that this process may not have occurred just once but could be eternal, producing endless, bubble universes. In this scenario, different regions of spacetime stop inflating at different times, giving rise to separate universes isolated from each other by ever-expanding space. Each bubble may have its own distinct physical laws, a consequence of symmetry breaking during inflation. This version of the multiverse, known as the inflationary or level 2 multiverse, implies that new universes are constantly forming, making reality far more expansive than we can observe. Quantum mechanics provides another line of reasoning that leads to a multiverse interpretation. According to the many worlds interpretation of quantum theory, every time a quantum event occurs with multiple possible outcomes, all outcomes happen but in separate, branching realities. For example, when a particle can exist in two states, instead of choosing one outcome, the universe splits into two, each realizing one possibility. This branching would occur constantly at every quantum interaction, creating an incomprehensibly vast tree of parallel worlds. In this view, there is not just one history of the universe but an infinite number of histories unfolding simultaneously, each as real as the one we experience. While elegant in some respects, this interpretation is deeply unsettling, as it suggests that every decision we make spawns countless alternative versions of ourselves in alternate universes. String theory, another cornerstone of modern theoretical physics, also predicts the possibility of multiple universes. String theory attempts to unify all fundamental forces and particles by modeling them as tiny vibrating strings existing in higher dimensional space. To make the mathematics work, string theory requires extra dimensions beyond the familiar 3 of space and 1 of time, possibly as many as 10 or 11 dimensions. These additional dimensions allow for a vast number of possible configurations or vacua, each corresponding to a universe with its own physical constants. Estimates suggest that the number of possible universes predicted by string theory could be as high as 10 to 500, an unimaginably large number. This collection of possible solutions is sometimes called the string landscape, and if these configurations are realized physically, they would form a multiverse of extraordinary diversity. Despite its intellectual appeal, the multiverse theory is controversial because it sits at the edge of science, where empirical verification becomes extremely difficult. By definition, other universes would lie beyond our observational horizon, inaccessible to any conceivable telescope or detector. This raises the question of whether the multiverse is a scientific hypothesis or a philosophical conjecture. Critics argue that a theory without testable predictions is not science, while proponents counter that the multiverse may be an unavoidable implication of theories that have already been partially confirmed, such as inflation and quantum mechanics. Some suggest that indirect evidence, such as patterns in the cosmic microwave background or signatures of collisions between bubble universes, might someday be detectable, but so far no such evidence has been found. The idea of a multiverse carries profound implications for our understanding of reality and our place in it. If the multiverse exists, then the notion of uniqueness, the idea that our universe is special, must be abandoned. Our cosmos would be just one variation among countless others, and the physical laws we regard as fundamental might be local rules, not universal truths. It would also redefine the concept of probability, as anything that can happen would happen somewhere. On a philosophical level, the multiverse forces us to confront deep questions. Are there infinite copies of us living different lives? Does this diminish the significance of individual existence? Or does it expand the horizon of what reality means beyond anything we can imagine? While the multiverse remains speculative, it reflects a natural progression of scientific thought. As our understanding of the cosmos grows, so too does our sense of its vastness. Whether the multiverse is ultimately confirmed, refuted, or forever beyond the reach of observation, it challenges us to rethink the nature of reality itself and reminds us that the universe, or universes, may be far stranger than we can conceive. Simulation hypothesis. The simulation hypothesis is a provocative idea that challenges the very nature of reality, suggesting that our universe, and everything within it, including the laws of physics, the stars, the Earth, and even our consciousness, might be part of an artificial simulation created by an advanced intelligence. Rather than existing in a fundamental, physical reality, we could be living inside a highly sophisticated virtual construct, comparable in concept to computer simulations we create today, but operating at an incomprehensibly vast and intricate scale. This hypothesis raises profound questions about the nature of existence, the limits of technology, and the reliability of human perception. The argument for the simulation hypothesis is most famously associated with philosopher Nick Bostrom, who formalized it in 2003. He did not claim that we are definitively in a simulation but presented a trilemma: at least one of the following propositions must be true. First, almost all civilizations at our level of technological development go extinct before reaching a post-human stage capable of running ancestor simulations. Second, even if such civilizations do survive, they are not interested in running a significant number of simulations of their evolutionary history. Third, we are almost certainly living in a simulation. The reasoning behind the third option is statistical. If advanced civilizations exist and can create simulations, and if they choose to run countless simulations, then the number of simulated realities would vastly outnumber the one base reality. Consequently, the probability that we are in the single base reality would be astronomically small compared to the probability that we exist in one of the many simulations. At the heart of this hypothesis lies the rapid progression of computing technology. Human civilization has already advanced from rudimentary mechanical calculators to supercomputers capable of modeling weather systems, quantum phenomena, and entire virtual environments in the span of a few centuries. The development of immersive virtual reality and artificial intelligence has further blurred the line between simulation and reality. If technological progress continues, it is plausible that future civilizations could possess computational power sufficient to simulate entire worlds down to the smallest detail, including the minds of conscious beings who believe themselves to be real. Given enough processing capacity, a sufficiently advanced civilization could simulate not only the observable universe but also the subjective experiences of every entity within it. This hypothesis draws strength from observations in physics that suggest reality might have an underlying computational structure. For example, the universe appears to be governed by discrete laws rather than continuous chaos, leading some theorists to speculate that physical reality resembles a vast information processing system. Concepts from quantum mechanics, such as the probabilistic nature of particles and the apparent role of observation in determining states, have been interpreted by some as evidence for a programmed or rendered reality. Furthermore, the speed of light as a universal limit, the pixel-like granularity suggested by Planck length, and the mathematical elegance of physical laws could be seen as indicators of a computational framework. However, the simulation hypothesis is not without significant objections. One major criticism concerns its falsifiability. If the simulation is perfect, there may be no empirical way to distinguish it from base reality, making it more of a philosophical speculation than a scientific theory. Some proponents argue that imperfections or glitches in the simulation could reveal its artificial nature, such as inconsistencies in physical laws or anomalies in fundamental constants. Others suggest that constraints like the maximum speed of information transfer or unexplained quantum phenomena might be artifacts of the simulation's architecture. Still, these ideas remain speculative, and no definitive evidence has been found. The hypothesis also faces philosophical challenges. If we are in a simulation, who created it and why? Possible motivations range from scientific curiosity, future beings running simulations to study their ancestors, to entertainment or even purposes beyond our comprehension. This line of thought mirrors theological questions about creation and design, leading some to describe the simulation hypothesis as a modern, technological version of ancient philosophical and religious ideas. Another question arises: if we are in a simulation, are the entities simulating us themselves simulated? This recursion leads to the unsettling possibility of an infinite hierarchy of simulated worlds, each unaware of its artificial nature. Despite its speculative nature, the simulation hypothesis has gained cultural prominence and even some attention in the scientific community. Prominent figures in technology and physics, such as Elon Musk and Neil deGrasse Tyson, have expressed that the probability of living in a simulation might be significant. Some researchers have proposed theoretical tests, such as detecting computational limits in the cosmos or anomalies in cosmic rays, but practical implementation remains elusive. In the absence of empirical evidence, the simulation hypothesis serves as a philosophical framework for questioning the nature of reality, rather than a testable scientific theory. The implications of the hypothesis, if true, would be staggering. It would mean that everything we perceive, the Earth, the stars, the history of humanity, and even our innermost thoughts, is part of a construct designed by an intelligence beyond our comprehension. This would redefine fundamental concepts such as existence, free will, and purpose. Conversely, even if the hypothesis remains unproven, it forces us to confront deep questions about consciousness, technology, and the limits of human knowledge. In this sense, whether or not we live in a simulation, contemplating the possibility reshapes our understanding of reality and our place within it. Big Bang Theory. The Big Bang Theory is the prevailing scientific explanation for the origin and evolution of the universe, describing a process that began roughly 13.8 billion years ago and continues to shape the cosmos today. At its core, this theory asserts that the universe originated from an extremely hot, dense, and compact state, a state so compressed that it defies our conventional understanding of space, time, and matter. This initial condition, often described as a singularity, contained all the energy and matter that would eventually give rise to stars, galaxies, planets, and life itself. Unlike an ordinary explosion that disperses material into pre-existing space, the Big Bang was an expansion of space itself. Space and time were created in this event, meaning there was no before in the traditional sense. In the earliest moments after the Big Bang, the universe underwent a phase known as cosmic inflation, a period of unimaginably rapid expansion occurring in less than a fraction of a second. During inflation, the universe grew exponentially, smoothing out any initial irregularities and creating the uniformity that we observe today in the large-scale distribution of galaxies. At the same time, quantum fluctuations, tiny variations in density at the smallest scales, were stretched to cosmic sizes, eventually seeding the formation of galaxies and clusters of galaxies. Inflation is a critical component because it explains why the universe appears so uniform in all directions while still containing small variations that led to cosmic structure. As inflation ended, the universe continued to expand, but at a slower rate, and began to cool. In the first millionth of a second, temperatures were so extreme that matter could not exist in its familiar form. Instead, the universe was a seething plasma of fundamental particles such as quarks, gluons, electrons, and neutrinos. Quarks combined to form protons and neutrons within the first microseconds. About 1 second after the Big Bang, these particles began interacting through nuclear forces, and neutrinos decoupled, streaming freely through space. Within the first few minutes, conditions allowed for nuclear fusion in a process known as Big Bang nucleosynthesis. This process produced the lightest elements, primarily hydrogen and helium, with trace amounts of deuterium and lithium. Heavier elements could not form at this stage because the universe cooled too quickly for the necessary reactions to occur, leaving their creation to later generations of stars. For the next 380,000 years, the universe remained a dense, hot plasma of nuclei, electrons, and photons. Photons, or light particles, were constantly scattered by free electrons, making the universe opaque. Only when the temperature dropped enough for electrons to combine with nuclei to form neutral atoms did the universe become transparent. This event, known as recombination, allowed photons to travel freely through space for the first time. Those ancient photons have been stretched by cosmic expansion into microwave wavelengths, forming the cosmic microwave background radiation, CMB, a faint glow that pervades the entire universe and serves as one of the strongest pieces of evidence for the Big Bang. Detected in 1965 by Arno Penzias and Robert Wilson, the CMB is a nearly uniform signal with tiny fluctuations that correspond to the seeds of cosmic structure, confirming predictions made by the theory. As billions of years passed, gravitational attraction caused matter to clump together, forming the first stars and galaxies. Inside stars, nuclear fusion created heavier elements, which were dispersed into space when massive stars exploded as supernovae, enriching the universe with the building blocks for planets and life. Galaxies assembled into clusters and superclusters, shaping the large-scale structure of the cosmos. Observations show that this process continues today, but with a surprising twist: the expansion of the universe is accelerating, driven by a mysterious component known as dark energy, which dominates the energy content of the universe. This discovery, made in the late 1990s, added a new layer of complexity to the Big Bang model, requiring refinements to account for this acceleration. The Big Bang theory rests on multiple lines of evidence that reinforce one another. First, the expansion of the universe, discovered by Edwin Hubble in the 1920s, demonstrated that galaxies are moving away from each other, implying that the universe was once much smaller and denser. Second, the observed cosmic microwave background provides a direct snapshot of the early universe, perfectly matching theoretical predictions. Third, the relative abundance of light elements, such as hydrogen and helium, aligns with the calculations from Big Bang nucleosynthesis. Together, these observations make the theory the most successful cosmological model to date. Despite its success, the Big Bang theory does not answer every question, and some of its implications remain controversial. The nature of the initial singularity is still a mystery because our current laws of physics, general relativity and quantum mechanics, cannot fully describe conditions at that scale. This has led to speculative ideas, such as quantum cosmology, string theory models, and multiverse scenarios, which suggests that the Big Bang may not have been the absolute beginning of everything but rather a transition from a previous state or one of many similar events. The cause of inflation is also unknown, and the nature of dark matter and dark energy, which together make up about 95% of the universe's content, remains elusive. These gaps drive ongoing research, and while the Big Bang theory explains how the universe evolved from a very early state, it does not fully explain why that state existed in the first place. Ultimately, the Big Bang theory represents one of the greatest achievements of modern science, uniting observations from astronomy, physics, and cosmology into a coherent narrative of cosmic history. It is a theory grounded in empirical evidence yet open to revision as new discoveries emerge, reflecting the dynamic and self-correcting nature of science itself. Snowball Earth Hypothesis. The Snowball Earth Hypothesis is a bold and controversial scientific idea that suggests our planet, at several points in deep geological history, may have been almost entirely or even completely covered in ice, transforming Earth into a frozen sphere for millions of years. This theory challenges conventional assumptions about the stability of Earth's climate and raises profound questions about the resilience of life under extreme conditions. It combines insights from geology, climatology, paleontology, and planetary science, making it one of the most interdisciplinary debates in Earth science. The idea emerged in the late 20th century, building upon puzzling geological evidence. Ancient rock formations from the Neo-Proterozoic era, roughly 720 to 635 million years ago, contain deposits known as tillites, sedimentary rocks formed by glaciers, found not only in regions that were near the poles but also in areas that would have been close to the equator at the time. These deposits are accompanied by striations on bedrock, characteristic of glacial movement, and are overlain directly by carbonate layers that indicate a sudden return to warm, tropical seas. The juxtaposition of glacial and tropical signatures in the same geological sequence suggested that ice once extended into low latitudes, followed by an abrupt and dramatic thaw. These findings could not easily be explained by conventional models of glaciation confined to polar regions, giving rise to the radical Snowball Earth hypothesis. The mechanics of a snowball Earth event are thought to involve runaway positive feedback in the planet's climate system. If global temperatures were to fall sufficiently, due to reduced greenhouse gases, changes in solar output, or continental arrangements that favored cooling, ice sheets would expand. Because ice has a high albedo, meaning it reflects most incoming sunlight, further ice growth would reduce Earth's absorption of solar energy, leading to additional cooling. This feedback loop could, in principle, spiral until ice covered nearly the entire surface, including oceans down to tropical latitudes. The planet would become a reflective, frozen ball with only minimal areas of open water, perhaps near geothermal vents or thin equatorial cracks in the ice. Such a frozen Earth, however, presents a paradox. How could life survive under these conditions? Critics of the hypothesis argue that a fully ice-locked planet would extinguish photosynthetic organisms, which rely on sunlight penetrating the surface. Proponents respond that microbial life could have persisted in refugia, pockets of open water, thin ice, hydrothermal vent ecosystems, or subsurface lakes beneath the ice cover. Extremophile organisms found today in Antarctic subglacial lakes and around deep-sea hydrothermal vents provide analogues for how ancient life might have endured during these global glaciations. Far from being annihilated, life may even have been driven to evolve resilience and adaptability in these harsh environments, setting the stage for later evolutionary breakthroughs. Equally striking is the theory's account of how Earth escaped from such a frozen state. During a snowball episode, volcanic activity would continue to release carbon dioxide into the atmosphere, but with the ocean sealed under thick ice, the normal process of CO2 removal by weathering of rocks and absorption into the ocean would be largely shut down. Over millions of years, greenhouse gases would accumulate to extreme levels, eventually overwhelming the cooling effect of the reflective ice. When warming finally broke the ice's grip, the thaw would have been rapid and catastrophic, leading to what is often described as a hothouse Earth aftermath. The overlying carbonate rocks found in the geological record are thought to be chemical precipitates formed when supercharged atmospheric CO2 levels, combined with suddenly warm oceans, created conditions for intense carbonate deposition. The Snowball Earth hypothesis is not without its detractors, and alternative models have been proposed. One is the slushball Earth model, which posits that while ice extended far into the tropics, it never fully sealed the oceans. Instead, narrow bands of open water near the equator may have provided refuges for marine life and allowed limited photosynthesis to continue. This scenario is considered more plausible by many, as it avoids the problem of explaining the survival of complex ecosystems through a total freeze. Another critique is that the geological evidence can sometimes be interpreted in multiple ways, and that not all glacial deposits from the Neo-Proterozoic unequivocally point to low-latitude glaciation. Despite the controversy, the Snowball Earth idea has gained attention because of its potential evolutionary significance. The Neo-Proterozoic era, when these events are thought to have occurred, immediately precedes the Cambrian explosion, the period around 541 million years ago when complex animal life rapidly diversified. Some scientists propose that the extreme selective pressures of snowball episodes may have acted as evolutionary bottlenecks, pushing microbial life to innovate and diversify once conditions improved. Others suggest that the accumulation of oxygen in the atmosphere during these times was linked to the survival strategies of photosynthetic organisms under icy conditions, paving the way for more complex life forms. Beyond Earth, the hypothesis also influences how scientists think about the habitability of other planets. If Earth could enter a snowball state and still support life, then icy worlds like Europa or Enceladus might harbor subsurface ecosystems. Similarly, exoplanets in distant star systems could experience global glaciations but remain habitable under the right conditions. Thus, the debate over Snowball Earth extends beyond Earth's past to the broader question of how life might persist across the universe. In essence, the Snowball Earth hypothesis is both a cautionary tale and a source of inspiration. It highlights the instability of Earth's climate system and the delicate balance of feedback loops that sustain habitability. At the same time, it underscores life's extraordinary resilience, showing how even the harshest planetary conditions may not extinguish it but instead prepare it for greater complexity. Whether Earth was once a frozen sphere or merely a slush ball with icy oceans, the hypothesis forces us to confront the fragility and adaptability of life in a cosmos shaped by extremes. Time is an illusion. What people mean by time is an illusion can be several different but related claims, so it helps to begin by untangling those senses before following the arguments and consequences. One claim is metaphysical, that the passage of time, the becoming, the flow from future to present to past, is not a fundamental feature of reality but a feature of our description or of emergent systems. A stronger claim is ontological, that there is no objective, temporal becoming, at all and that all events, past, present, and future, are equally real in a tenseless four-dimensional structure, the so-called block universe. A still stronger, and more technical, claim is that time does not exist at the most fundamental level of physical law. The deepest equations that govern the cosmos are timeless, and what we call time emerges only in approximate, coarse-grained descriptions. Often these ideas are bundled together under the slogan, "Time is an illusion," but each requires a different set of arguments and has different philosophical costs. Relativity supplies the first major set of reasons to doubting the common-sense picture of time. In Newtonian physics, a universal present is imagined, a cosmic snapshot that all observers can agree on. Special relativity destroys that picture. Simultaneity is relative to the observer's state of motion. Two events judged simultaneous by one observer will in general not be simultaneous for another. If there is no observer independent now, then the notion of a universal flowing present loses its natural grounding. From this moves the case for the block universe. If spacetime is a four-dimensional manifold in which time is just another coordinate, then past, present and future can be viewed as different regions of a single, fixed spacetime. In that view, the passage of time is not a dynamical feature of the world but a feature of how creatures embedded in that manifold experience sequences of events. Einstein himself wrote and reacted in ways that encourage taking this tenseless view seriously. If simultaneity is not absolute, why privilege a present slice of spacetime as metaphysically real? Philosophy has formalized these competing views in terms of A theory and B theory, or presentism versus eternalism. A theorists insist the distinction between past, present, and future is fundamental. The present is metaphysically privileged and genuine becoming occurs. B theorists deny that becoming has ontological weight. They treat temporal relations, earlier than, later than, as tenseless orderings. McTaggart famously argued that the A series, past/present/future, is contradictory and that time therefore is unreal. Whether that conclusion follows depends on subtle metaphysical moves, but the argument highlights that ordinary intuitions about a flowing time face serious conceptual pressure once the relativity of simultaneity and formal logic are brought to bear. A separate but closely connected line of argument comes from modern theoretical physics, especially quantum gravity. In many canonical approaches that try to combine quantum mechanics and general relativity, time disappears from the fundamental equations. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, famously lacks a time parameter. The wave function seems frozen. That leads to the problem of time. How does a timeless fundamental equation yield the manifest temporal evolution we see? Some researchers propose that time is emergent, an approximate parameter that appears when one subsystem is used as a clock relative to which another subsystem evolves. The Page-Wouters mechanism formalizes this idea. Correlations between degrees of freedom allow one to recover ordinary Schrödinger time from a globally static state. Other proposals, such as the thermal time hypothesis, argue that thermodynamic conditions, KMS states, statistical structure, endow a preferred notion of time with physical meaning. Julian Barber, in a different vein, argues for a landscape of timeless nows, configurations, with apparent motion arising from ordering relations among them. For Barber, the universe is a set of configurations and the feeling of time is a feature of certain sequences in that configuration space. These proposals do not yet constitute a single, empirically verified theory, but they show there are consistent ways in which time can be reconstructed from non-temporal microphysics. If time is not fundamental, why do we experience it so vividly as a flowing present? Neuroscience and psychology supply an explanation. The brain constructs a temporally extended, specious present by integrating incoming sensory signals, maintaining short-term memory, and predicting immediate outcomes. Perception imposes direction and continuity on a world of discrete events because brains evolved to anticipate, coordinate actions, and build narratives. Memory is asymmetric. We remember past states but not the future, and that asymmetry is tightly connected to thermodynamics. The second law of thermodynamics, which says entropy tends to increase, gives us a macroscopic arrow of time. The past hypothesis, the empirical fact that the early universe had extremely low entropy, anchors this arrow. Because the early universe started in a special low entropy state, entropy increases and processes are temporally asymmetric. You can scramble an egg but can't unscramble it. That statistical, entropic irreversibility explains why records and memories form only toward the future and why causes seem to precede effects in our experience. Thus, even if at the microphysical level the laws are time-symmetric, the macro level manifests a clear temporal direction due to boundary conditions and statistical facts. Sewing these threads together yields a hybrid picture. The fundamental description may be tenseless or even timeless, while thermodynamic and cognitive processes produce the effective, directional time we live by. From the block universe perspective, the flow of time is an emergent, epistemic feature, a real subjective aspect of minds embedded in spacetime but not a feature of the ontology itself. From the timeless quantum gravity perspective, the world's basic lawbook contains no time label, but subsystems can serve as relational clocks so that effective time emerges for observers within the universe. There are robust objections and philosophical repercussions to this illusion claim. Many find the loss of an objective passage unacceptable because it seems to gut free will and moral responsibility. If the future is just as real as the past, how can our choices make a difference? A variety of responses exist. Compatibilists argue that free will is compatible with tenseless ontology. Agency is understood in terms of processes and dispositions that are embedded in the four-dimensional block. Others deny that tenselessness eliminates responsibility because actions are still part of the block and causal relations between events are preserved. Moreover, even if the future exists in a static sense, our epistemic access to it is limited, and that limitation is sufficient for moral practice. Empirical arguments also complicate the claim. Special relativity undermines naive presentism but does not logically force tenselessness. Some sophisticated presentist views attempt to reconcile a privileged present with relativity by positing preferred foliations or novel metaphysical structures, though these often sacrifice the spirit of relativity or add unwelcome structure. Conversely, a strictly timeless fundamental theory must show how to recover the rich and specific temporal phenomenology we measure: clocks, decay rates, cosmological evolution, gravitational waves, and so on. Derivations like Jacobson's result, deriving Einstein's equations from thermodynamic assumptions about horizons, suggest an intimate link between thermodynamics, information, and geometry, strengthening the case that macroscopic temporal behavior can arise from deeper, non-temporal facts, yet constructing a complete, empirically adequate emergent account remains an open program. There are also intermediate positions. Relationalists insist time is nothing over and above relations among events or processes. Time is a label for change, not an independent substance. That squares well with operational physics. Time is what clocks measure, and yet it keeps open the view that temporal ordering is real even if there is no absolute flow. Other philosophers emphasize pragmatic or epistemic readings of illusion. The passage of time may be illusory in the metaphysical sense but entirely real as a phenomenological or emergent fact. That is, illusion need not mean false, it can mean not fundamental. What would it take to settle the issue? Ultimately, answers will come from both metaphysical clarity and physical evidence. Quantum gravity progress could show whether the deepest equations include a fundamental time parameter or not, and cosmological conditions might illuminate why macroscopic time arrows point uniformly in one direction. Neuroscience can map how brains construct temporal experience, strengthening the explanatory link between physical asymmetries and subjective passage. For now, time is an illusion is best read as a collection of serious, partly supported claims. Our experienced flow of time is not necessarily a primitive property of the cosmos. Relativity and many approaches to quantum gravity undermine the classical notion of an absolute present, and thermodynamics and cognition plausibly account for the arrows and felt passage that characterize our lives. Those conclusions do not make time irrelevant. Whether fundamental or emergent, temporal structure underpins causation, prediction, and explanation in science. Even if the flow we feel is a construction, it is an indispensable construction, one that both shapes action and must be matched by any correct physical theory. The suggestion that time is an illusion is not an invitation to nihilism but a daring reorientation. It asks us to see time the way physics increasingly invites us to see many familiar things, as patterns that emerge from deeper relations, as constraints on information and history, and as phenomena whose reality is measured by the explanatory and predictive power of the accounts that recover them. If time is not what it seems, the challenge is to tell the story of how it arises, and to do so in a way that preserves the empirical facts we rely on when we set clocks, remember the past, and make plans for the future. Expanding Earth Hypothesis. The expanding Earth hypothesis is an idea that once attracted serious attention from a minority of geoscientists and a larger circle of enthusiasts because it offered an intuitively simple way to explain how continents fit together and why mountain chains, ocean basins, and continental margins look the way they do. Rather than accepting that Earth's surface is rearranged by plates that move, collide, slide past one another and sink back into the mantle, the expanding Earth picture replaces that machinery with a single global process. The planet's radius has grown through geological time. On a smaller Earth, the continents were once contiguous. An early configuration of the crust looked like a single world-covering shell, and as the planet enlarged, that shell cracked and the fragments drifted apart, producing ocean basins and the present distribution of continents. This idea has two parts, an observational claim and an explanatory mechanism. Observationally, proponents point to three kinds of apparent facts. First, the snug geometric fit of continental margins, famously illustrated by the correspondence between South America and Africa, looks easier to explain if those continents were gently pulled apart by planetary expansion rather than ripped and reassembled by plate motions. Second, the apparent shortage of very old oceanic crust, most seafloor is younger than about 200 million years, could be read, in an expanding Earth narrative, as meaning ocean basins are newly created as the globe grows rather than being continually recycled by subduction. Third, some global tectonic patterns, symmetric rift systems, belts of volcanism, and broad uplift, can, at a superficial level, be fitted into a story of the crust cracking and stretching as the planetary circumference increases. Historically, the idea has an older pedigree. In the early 20th century, a handful of geologists, notably Christoph Hilgenberg and later S. Warren Carey among others, developed the notion more fully, proposing that the radius of the Earth was substantially smaller in the distant past and that continents were once a continuous shell that cracked as the planet expanded. Carey and his followers made detailed paleogeographic reconstructions, arguing that a steadily enlarging planet could account for continental drift without invoking subduction. In the pre-1960s context, when the mechanisms for continental motion were incompletely understood and plate tectonic evidence was still accumulating, expansion seemed at least plausible to some. To turn that broad brush picture into a physical theory, proponents have suggested various mechanisms for how the Earth could grow. A few of the mechanisms historically advanced are these: continuous accretion of interplanetary dust and meteorites adding mass, internal phase changes, for example, conversion of denser to less dense mineral phases that increase volume without increasing mass, thermal expansion of the interior, production of new matter from some exotic internal process, or the release of stored mechanical or chemical energy that somehow forces the solid globe to swell. In the later 20th century, some more exotic suggestions invoked changes in fundamental constants or novel physics to provide the extra mass-energy budget. These proposals are heterogeneous, and their common problem is that they must supply enormous amounts of energy or mass, and produce testable consequences that are not observed. Examined against modern evidence and physical constraints, the expanding Earth hypothesis runs into multiple, decisive difficulties. First, plate tectonics provides a coherent, highly predictive framework that explains an extremely broad range of observations: the matching of paleomagnetic stripes on the seafloor with seafloor spreading, the progressive age pattern of oceanic crust moving away from mid-ocean ridges, earthquake patterns locating subduction zones and transform faults, the occurrence of volcanic arcs and deep-sea trenches, tomography images of subducted slabs penetrating the mantle, and the quantitative fit of relative plate motions measured by geodesy. The expanding Earth story must either replicate all of those explanations or show why they are misinterpreted. It has not done so. Second, direct geodetic observations in the satellite era have become very precise. Global Positioning System, GPS, Very Long Baseline Interferometry, VLBI, satellite laser ranging, and altimetry now measure plate motions and global shape changes to millimeter per year precision. These techniques show plate separation, convergence, and transform motion consistent with plate tectonics and, crucially, no statistically significant secular increase of Earth's mean radius on the large scale required by classical expanding Earth models. Were the planet's radius increasing by kilometers over geologic time, modern geodesy and satellite altimetry would detect a secular radial trend. They do not. The tiny secular signals that are seen are accounted for by post-glacial rebound, mass redistribution, and elastic deformation, processes that operate on regional or transient timescales, not a global, secular planetary inflation. Third, conservation laws and energetics impose very strong constraints. A modest global expansion produces measurable changes in moments of inertia and in gravitational binding energy. For example, consider a thought experiment often used in critiques. If Earth's radius had increased by 5% since some past epoch, the volume would grow by about 1.05 superscript 3-1 is equal to 0.157625, or roughly 15.76%. Such an increase in radius changes the planet's moment of inertia by a factor of 1.05 superscript 2 is almost equal to 1.1025. If angular momentum is conserved, this would lengthen the day by about 10.25%, more than 2 hours compared to the present 24-hour rotation. Geological proxies for paleorotation, tidal rhythmites, growth banding in corals and stromatolites, and other paleontological indicators do show a lengthening day over geologic time, but at rates attributable to tidal friction with the Moon, and not the enormous stepwise or continuous change that a large radius increase would demand. Moreover, the change in gravitational binding energy associated with even a 5% radial growth is enormous, on the order of 10 to 31 joules for a uniform sphere estimate, many billions of times the Earth's present annual geothermal output, supplying that energy from any plausible internal or external source is not feasible within known physics. Fourth, independent lines of geological and geophysical data support subduction rather than wholesale surface area creation without destruction. Earthquakes plunge down subduction zones in coherent Wadati-Benioff belts. Oceanic lithosphere older than -200 million years is virtually absent because it is recycled into the mantle at trenches. High-pressure metamorphic rocks and accretionary complexes along continental margins record the underthrusting and burial of oceanic and continental material. Seismic tomography images cold high-velocity slabs descending into the mantle at depths of hundreds to thousands of kilometers. These are not easily accommodated by a model that forbids or ignores consumption of lithosphere. Fifth, the chemistry and mass balance arguments are unfavorable. If new crustal area is continuously produced to satisfy an expanding planetary skin, then either mass must be added to maintain mean density, or density must fall. The observed mean density of Earth, -5.5 g/cm superscript 3, and the planet's mass, well measured by orbital mechanics, do not indicate any secular mass increase of the kind required. Accreting enough interplanetary dust to account for kilometer-scale radius growth would be visible in other ways and is quantitatively insufficient. Similarly, mechanisms invoking creation of matter confront deep issues about energy conservation and the absence of astrophysical signatures that would accompany such creation. Sixth, a viable theory must explain the magnetic and paleomagnetic record. The history of Earth's magnetic field, geomagnetic reversals recorded in volcanic rocks and in seafloor magnetic stripes, fits naturally with plate spreading and polarity chronologies. Expanding Earth advocates who rejected seafloor spreading had to reinterpret these patterns, but such reinterpretations generally require more complex ad hoc assumptions than the plate tectonic accounts. For all these reasons, by the 1970s and 1980s, as the plate tectonics paradigm matured and the wealth of quantitative, converging evidence accumulated, the mainstream geological community abandoned the expanding Earth hypothesis as a serious alternative. It survives only as a fringe idea and occasionally resurfaces in popular treatments or among a small number of researchers who either attempt to identify new mechanisms or reinterpret the data. Modern proponents must contend with the observational power of space geodesy, seismic imaging of mantle structure, and a global body of paleomagnetic and stratigraphic evidence that plate tectonics explains with unity and economy. That said, the expanding Earth discussion played a useful historical role. It pushed geoscientists to sharpen their arguments, quantify expectations, and develop the very observational techniques that ultimately resolved the debate. From a philosophy of science perspective, it illustrates how empirical constraints, conservation principles, and predictive coherence narrow the field of acceptable theories. An idea that looks simple and attractive at a conceptual level can be rejected once the full suite of data and physical laws is considered. If one tries to salvage some weakened, more technical variants of expansion, they typically do so by localizing the effect or tying it to other, better established processes, thermal uplift, transient episodes of lithospheric inflation due to mantle plume activity, or local magmatic underplating, rather than positing a global, secular increase in planetary radius. Those localized processes are real and studied within mainstream tectonics. They do not imply a whole Earth growth. In short, the expanding Earth hypothesis is an historically interesting and at times mathematically or geometrically suggestive idea that ultimately fails to account for the diverse, high-precision observations and basic physical constraints we now possess. Plate tectonics, backed by seafloor age patterns, paleomagnetism, earthquake seismology, mantle tomography, and precise geodetic monitoring, provides a far more successful and economical explanation of the planet's evolving surface. The expanding Earth picture remains a cautionary tale about how attractive intuitions must yield to rigorous, multidisciplinary evidence. White hole theory. The white hole theory describes a hypothetical region of spacetime that acts as the reverse of a black hole. While a black hole is a region where gravity is so strong that nothing, not even light, can escape, a white hole is a region from which nothing can enter, yet matter and energy can only emerge. In essence, a white hole would be a cosmic fountain, continuously expelling matter and radiation while remaining impervious to external intrusion. This concept arises naturally from the mathematical equations of general relativity, which allow for solutions that mirror black holes but with time reversed. If black holes represent extreme gravitational collapse and an inescapable future for anything crossing the event horizon, then white holes represent a state of perpetual ejection, an origin point rather than an end point. The theoretical foundation for white holes was first recognized in the context of the Schwarzschild solution to Einstein's field equations. The Schwarzschild metric, which describes the geometry of spacetime around a spherically symmetric, non-rotating mass, contains two distinct regions when extended to include all possible coordinates, one corresponding to a black hole and another corresponding to a white hole. In this idealized extension, the black hole and the white hole are connected through what is known as an Einstein-Rosen bridge, or wormhole, forming a complete Schwarzschild spacetime. Matter could theoretically enter the black hole region, travel through the bridge, and emerge from the white hole region. However, this structure is unstable. Any small disturbance would cause the wormhole to collapse before anything could traverse it. Nonetheless, the existence of these solutions sparked interest in the physical interpretation of white holes. A white hole would have an event horizon, similar to that of a black hole, but with the causal structure reversed. For a black hole, the event horizon marks a boundary beyond which no information or matter can escape. For a white hole, it marks a boundary beyond which nothing can enter. Observers outside a white hole would see material emerging from its horizon, but no particle or signal could ever cross the horizon from the outside. This makes white holes fundamentally time asymmetric. They behave as though the arrow of time points outward from their center, in contrast to black holes, where the arrow of time points inward. One intriguing idea is that white holes could be linked to black holes through time reversal symmetry. In this interpretation, the formation of a black hole in the future corresponds to the existence of a white hole in the past. From this perspective, the Big Bang, the event that marked the origin of our universe, shares properties with a white hole. It was an event from which all matter and energy emerged, and nothing prior to it appears to influence what came afterward. Some cosmologists have speculated that the Big Bang could be interpreted as a massive white hole, although this analogy remains speculative because the global structure of spacetime in cosmology differs from that of an isolated Schwarzschild solution. The theory of white holes also appears in discussions of quantum gravity and the ultimate fate of black holes. According to classical general relativity, anything falling into a black hole is lost to the outside universe forever, but quantum mechanics forbids the destruction of information. This tension underlies the black hole information paradox. Some proposals suggest that after an extremely long period of Hawking radiation, a black hole could evaporate and transition into a white hole, expelling the information it once absorbed in a scrambled form. This scenario offers a possible mechanism for preserving information without violating the principles of quantum mechanics. Researchers in loop quantum gravity, for example, have proposed models where quantum effects near the singularity cause a bounce, turning the black hole interior into a white hole and releasing matter back into the universe after a vast span of time. Despite these theoretical possibilities, no observational evidence for white holes exists. And many physicists doubt they could ever form naturally in our universe. Unlike black holes, which arise from gravitational collapse, white holes have no known formation mechanism that aligns with the laws of thermodynamics. A white hole that continuously emits matter and energy without absorbing anything would seem to decrease entropy, violating the second law of thermodynamics. Additionally, any real astrophysical environment is full of matter and radiation, and a white hole's defining property, that nothing can enter, would make it highly unstable if exposed to even the slightest perturbation. For these reasons, most physicists regard white holes as mathematical curiosities rather than physically plausible objects. Nevertheless, the concept of white holes persists in theoretical discussions because it touches on deep questions about time, causality, and the nature of spacetime. If black holes represent regions where time effectively ends for infalling matter, white holes would represent regions where time begins. This duality resonates with the broader quest to understand whether the laws of physics are fundamentally time-symmetric or whether the arrow of time emerges from boundary conditions imposed at the universe's origin. Even if white holes never exist as actual astrophysical objects, the idea that they could exist according to the equations of general relativity reminds us that our intuitive notions of space, time, and causality may be incomplete. Some speculative hypotheses go further, suggesting that every black hole might eventually give rise to a white hole in another region of spacetime, or even in a new universe, connected by a wormhole-like structure. In these scenarios, black holes are not merely cosmic sinks but also potential gateways to other realms. While such ideas remain beyond the reach of observation, they illustrate how the white hole concept continues to inspire new ways of thinking about the cosmos. Electric universe theory. The electric universe theory is a controversial framework in modern science that challenges many of the foundations of mainstream astrophysics and cosmology. It proposes that electricity and plasma phenomena, rather than gravity alone, play the dominant role in shaping the structure and dynamics of the universe. While conventional science describes the cosmos as governed primarily by gravitational forces, nuclear fusion, and relativistic effects, the electric universe school argues that vast networks of electrical currents, carried by plasma, the most abundant form of matter in the universe, are responsible for many of the large-scale features we observe, from galaxies and stars to planetary systems. This perspective is considered fringe within the scientific community, but it has attracted interest among certain researchers, engineers, and independent thinkers who see in it a more unified explanation of cosmic processes. At the heart of the electric universe hypothesis lies the behavior of plasma. Plasma is a state of matter consisting of charged particles, ions and electrons, that can conduct electricity and respond to electromagnetic fields. In laboratories and on Earth, plasma exhibits complex, filamentary structures and dynamic patterns when currents flow through it. Proponents of the electric universe argue that similar processes occur on cosmic scales. They suggest that interstellar and intergalactic space, far from being empty voids, are filled with tenuous plasma threaded with electric currents. These currents, according to the theory, form vast, filamentary networks sometimes referred to as Birkeland currents, named after the Norwegian scientist Christian Birkeland, who in the early 20th century studied the aurora borealis and discovered that charged particles guided by Earth's magnetic field produced the phenomenon. Electric universe advocates extend this principle to the cosmos itself, claiming that such currents organize galaxies, power stars, and shape planetary environments. One of the theory's most provocative claims concerns the nature of stars. In mainstream astrophysics, stars shine because of nuclear fusion in their cores, where immense gravitational pressure allows hydrogen atoms to fuse into helium, releasing vast amounts of energy. The electric universe, however, posits that stars are instead powered externally by electric currents flowing through galactic plasma. In this view, stars function as anodes, drawing in current from surrounding space, and their light and heat are the result of electrical discharges rather than nuclear reactions. If true, this would overturn a century of astrophysical theory, rewriting the understanding of stellar life cycles, supernovae, and even the origins of heavy elements. The theory also offers alternative explanations for cosmic structures such as galaxies. Mainstream cosmology relies on the concepts of dark matter and dark energy to explain why galaxies rotate faster than visible matter alone would allow, and why the universe's expansion is accelerating. Electric universe proponents argue that these phenomena may not require invisible substances. Instead, they propose that electromagnetic forces, which are vastly stronger than gravity on the particle scale, could explain galactic dynamics without invoking dark matter. The filamentary patterns of galaxies, galaxy clusters, and cosmic web structures are, in their view, evidence of plasma currents on the largest scales, channeling matter along electromagnetic pathways. On a smaller scale, electric universe theorists often point to planetary science and ancient mythology as supporting evidence. They claim that many planetary features, such as craters, rills, or unusual surface patterns, are better explained by electrical discharge machining than by impacts or tectonic activity. For example, they argue that some craters have shapes inconsistent with meteor strikes but resemble scars produced by high-voltage discharges in plasma experiments. Furthermore, some adherents link ancient myths, petroglyphs, and religious symbols to plasma phenomena in the sky, suggesting that early humans witnessed large-scale electrical events between planets or within Earth's atmosphere. This fusion of cosmology with archaeology and mythology adds to the theory's controversial character, as it bridges science with interpretations of human history. Critics of the electric universe dismiss it as pseudoscience, pointing out that it lacks rigorous mathematical models, quantitative predictions, and peer-reviewed validation. The established understanding of stars, for example, is supported by extensive evidence from spectroscopy, neutrino detection, and models that accurately describe stellar evolution and supernova behavior. Similarly, plasma physics is already an accepted part of astrophysics, but mainstream scientists argue that while plasma and electromagnetic forces are important in certain contexts, such as solar flares, auroras, and the behavior of the interstellar medium, they do not replace gravity as the dominant force shaping galaxies and stars. Detractors also note that the electric universe often relies on visual similarities between laboratory plasma discharges and cosmic structures, without demonstrating physical equivalence through detailed equations and models. Despite these criticisms, the electric universe theory persists in alternative science communities because it appeals to intuition and offers simple, visually compelling explanations for complex cosmic phenomena. It emphasizes observable plasma behavior, laboratory replication, and skepticism toward concepts like dark matter, dark energy, and black holes, which, while widely accepted in cosmology, remain indirect and difficult to detect. For some, the theory represents a refreshing challenge to orthodoxy, highlighting the value of questioning assumptions and exploring unconventional ideas. For others, it serves as a cautionary tale about the boundary between genuine scientific inquiry and speculative interpretation. Ultimately, the electric universe is controversial because it strikes at the foundations of modern astrophysics. If correct, it would demand a radical rethinking of how stars shine, how galaxies form, and how the universe itself operates. If incorrect, it underscores the resilience of mainstream models that have withstood experimental and observational testing. Either way, it raises profound questions about the nature of scientific progress, whether it proceeds only through the slow accumulation of consensus or also through disruptive, outsider ideas that force established fields to re-examine their assumptions. Retrocausality in quantum mechanics. Retrocausality in quantum mechanics is a deeply intriguing and controversial concept that challenges one of the most fundamental intuitions about reality, that causes precede their effects in time. According to retrocausal interpretations, events in the future can influence, determine, or constrain events in the past at the quantum level. This notion runs counter to classical causality, which dictates a unidirectional arrow of time flowing from past to future. Retrocausality suggests that the underlying fabric of quantum reality may not share the same temporal asymmetry that governs our macroscopic experience. Instead, it proposes a more symmetric view of time, where influences can propagate both forward and backward, consistent with the time-reversible nature of many fundamental physical laws. The origins of retrocausality as a serious idea in physics stem from the peculiarities of quantum theory, especially the measurement problem and the non-local correlations revealed by Bell's theorem. In quantum mechanics, particles such as electrons or photons can exist in superpositions of states, and their properties, like spin or polarization, are not determined until a measurement is made. When entangled particles are measured at distant locations, the outcomes are correlated in a way that defies classical explanation. Standard interpretations, such as the Copenhagen interpretation, assert that the act of measurement collapses the wave function, seemingly creating definite outcomes from indeterminate possibilities at the moment of observation. However, this interpretation does not explain how correlated outcomes occur without faster-than-light communication, which relativity forbids. Retrocausal interpretations provide an alternative. Instead of invoking instantaneous influence across space, they allow future measurement choices to influence the earlier quantum state, ensuring consistency without violating relativistic locality. One of the earliest formulations of retrocausality appeared in the 1940s with the Wheeler-Feynman absorber theory, which proposed a time-symmetric approach to electromagnetism. In this theory, electromagnetic radiation consists of both retarded waves, traveling forward in time, and advanced waves, traveling backward in time. While in practice the retarded solutions dominate, the inclusion of advanced waves showed that fundamental equations permit backward-in-time effects. This idea later inspired time-symmetric interpretations of quantum mechanics, including the two-state vector formalism developed by Yakir Aharonov, Peter Bergman, and Joel Leibowitz in the 1960s. In this approach, a quantum system is described not by a single state evolving from the past but by two states, one evolving forward from the past and another evolving backward from the future, meeting at the point of measurement. The present state of the system thus depends on boundary conditions at both ends of time, making the future just as relevant as the past. Retrocausality also offers an alternative perspective on quantum paradoxes such as the delayed choice experiment and the quantum eraser. In the delayed choice experiment, first suggested by John Wheeler, the decision to observe a particle as a wave or a particle is made after the particle has entered the experimental setup. Astonishingly, the outcome behaves as if the particle knew in advance what kind of measurement would be made, even though the decision occurs later in time. Similarly, in the quantum eraser experiment, information about a particle's path can be erased after detection, retroactively restoring interference patterns that would otherwise disappear. Conventional interpretations explain these results by emphasizing that quantum properties are undefined until measured, but retrocausality interprets them as evidence that future measurement choices can influence the past quantum state. Mathematically, retrocausality fits comfortably within the formalism of quantum theory because the Schrödinger equation and other fundamental equations of physics are time-reversal symmetric. There is nothing in these equations that mandates a forward-only flow of influence. The arrow of time that we experience in everyday life arises from thermodynamics and the statistical tendency toward increasing entropy, not from the microscopic laws themselves. Retrocausal models exploit this symmetry, suggesting that the universe at the quantum level is best understood as a block structure, where past, present, and future coexist, and events are determined by boundary conditions at both temporal ends. This perspective aligns with the block universe view of spacetime in relativity, where time is another dimension, and the entire history of the universe exists as a static four-dimensional structure. Despite its elegance and potential to resolve some interpretational puzzles, retrocausality is controversial because it appears to undermine intuitive notions of free will and causation. If future events can influence the past, then do our present choices exist as genuine choices, or are they predetermined by future boundary conditions? Some proponents argue that retrocausality does not eliminate agency. Instead, it reframes causation as a global constraint rather than a local chain of events. Rather than imagining signals traveling backward in time, one can think of quantum processes as satisfying conditions imposed by both past and future, much like a solution to a mathematical equation that must meet constraints at 2 points. From this standpoint, retrocausality is not about changing the past but about the past and future being interdependent within a timeless structure. Another source of controversy lies in the lack of direct empirical evidence. Retrocausal interpretations are consistent with existing quantum experiments, but so are many other interpretations, including the Copenhagen interpretation, many worlds, and pilot wave theory. No current experiment decisively proves that influences flow backward in time rather than being encoded in hidden variables or branching universes. Some physicists have proposed experiments to distinguish retrocausality from other interpretations, often involving quantum information protocols or post-selected systems, but these remain in the realm of theoretical possibility rather than practical implementation. Still, retrocausality has profound implications for the foundations of physics and philosophy. It invites us to rethink the nature of time, causality, and reality itself. If the universe is fundamentally time-symmetric and the future participates in shaping the present, then our linear, forward-moving perception of time may be an emergent feature of consciousness rather than a fundamental truth. This interpretation also offers a conceptual bridge between quantum mechanics and relativity, as both would then share a timeless, block-like ontology. Whether retrocausality represents a deep insight into the nature of reality or a conceptual detour remains an open question, but its very possibility illustrates the richness and strangeness of the quantum world. Gaia Hypothesis. The Gaia Hypothesis is one of the most provocative and imaginative attempts to rethink the relationship between life and its planetary environment. Proposed in the 1970s by the British scientist James Lovelock, with significant elaboration by microbiologist Lynn Margulis, the hypothesis suggests that the Earth functions as a self-regulating system in which living organisms interact with the atmosphere, oceans, soils, and climate in ways that maintain conditions favorable for life. Rather than treating life as a passive passenger on a planet governed purely by physics and chemistry, Gaia reframes the biosphere as an active participant in shaping and stabilizing its own environment. It is a vision of Earth as an integrated, quasi-living system. At its core, Gaia begins with a simple observation: Earth's environment has remained remarkably stable and habitable for billions of years, despite enormous external and internal forces that could have made it hostile to life. The sun has brightened by roughly 30% since the early Earth, yet global surface temperatures have remained within ranges that allowed liquid water and biological evolution. The atmosphere, too, has maintained a mixture of gases, oxygen, nitrogen, carbon dioxide, and trace elements, that is chemically out of equilibrium yet remarkably stable. Lovelock asked whether life itself might be playing an essential role in this homeostasis. The hypothesis proposes feedback loops between life and the environment. Organisms change their surroundings, and those changes can stabilize the very conditions that allow the organisms to thrive. For example, photosynthetic microbes and plants release oxygen, which enables complex life while also influencing atmospheric chemistry. Oceanic plankton emit dimethyl sulfide, which seeds cloud formation and affects planetary albedo, thereby modulating climate. Forests regulate water cycles through evapotranspiration, influencing regional and even global rainfall. Soil microbes recycle nutrients such as nitrogen and phosphorus, sustaining fertility and productivity. These processes, when viewed together, create a network of interactions that behaves like a planetary-scale control system, adjusting variables to keep Earth's conditions within ranges conducive to life. Lovelock captured this idea with the metaphor of Gaia, the ancient Greek goddess of Earth. But his proposal was not meant as mystical anthropomorphism, it was an attempt to apply systems thinking to planetary biology. He developed a mathematical model known as Daisy World to illustrate the concept. In Daisy World, only black and white daisies exist. Black daisies absorb heat, warming the planet, white daisies reflect sunlight, cooling it. The proportion of each species shifts as temperatures rise or fall, creating a self-regulating balance that stabilizes planetary temperature over a wide range of solar input. While simplistic, the model shows how life-environment feedbacks could generate stability without conscious design, purely through ecological dynamics. Despite its elegance, the Gaia hypothesis has been controversial from its inception. Critics in the scientific community argued that Lovelock's early formulations implied teleology, that the Earth intentionally maintains life-friendly conditions. From a Darwinian perspective, natural selection operates on organisms, not on the planet as a whole. There is no mechanism for selection at the level of Earth's biosphere. Evolutionary biologists worried that Gaia smuggled purpose into nature, which could blur the line between science and metaphysics. Lovelock responded by clarifying that Gaia does not require purpose or foresight. Self-regulation can emerge from countless local interactions between organisms and environment, just as ecosystems stabilize without any central controller. Over time, versions of Gaia were refined into weaker and stronger forms. The strong version posits that life collectively regulates the planet in a way that ensures habitability, almost as though Earth were alive. The weak version, now more widely accepted, suggests that life significantly influences planetary processes, sometimes enhancing stability but not guaranteeing it. In this weaker sense, Gaia is not mystical but ecological. Earth's biosphere modifies its environment, and some of those modifications promote long-term habitability. The distinction is important, because while scientists can study feedback loops empirically, they cannot test metaphysical claims of Earth's intentions. Evidence for Gaia-like processes is substantial, though not always decisive. Oxygen in the atmosphere, a byproduct of cyanobacterial photosynthesis billions of years ago, transformed Earth's chemistry and climate, paving the way for multicellular life. The carbon cycle, in which organisms help draw down CO2 and sequester it in sediments, interacts with volcanic outgassing and weathering in ways that stabilize climate over geologic timescales. Marine plankton influence cloud formation and radiation balance, while wetlands and soils regulate methane concentrations. These are genuine planetary-scale feedbacks involving life. Whether they amount to a coherent self-regulatory system or simply a collection of contingently stabilizing processes is the heart of the debate. Beyond the scientific arguments, Gaia resonated deeply with cultural and environmental movements. It offered a powerful metaphor for ecological interdependence, inspiring environmental ethics that emphasize humanity's embeddedness within a larger living system. For some, Gaia became a symbol of planetary stewardship, encouraging the view that harming ecosystems destabilizes the very conditions that support civilization. Lovelock himself later warned about human-driven climate change as a disruption to Gaia's regulatory balance, suggesting that the Earth system may respond in nonlinear ways to anthropogenic stresses. Yet Gaia also remains a scientific research program, not just a metaphor. The field of Earth system science, which emerged in the late 20th century, studies the coupled dynamics of atmosphere, biosphere, hydrosphere, and lithosphere in precisely the integrative way that Gaia anticipated. While mainstream scientists avoid anthropomorphic language, many accept that life has been a planetary-scale force shaping climate and chemistry for billions of years. Astrobiologists, too, draw on Gaia when asking how biospheres and planets co-evolve, and whether life elsewhere in the universe would leave similar planetary-scale signatures detectable from afar. In summary, the Gaia hypothesis is controversial because it straddles the line between science and metaphor, between systems theory and holistic imagery. Its boldest versions, implying the Earth acts as a single organism, are scientifically problematic because they imply selection and purpose at a planetary scale. But its more moderate formulations, that life and environment form a coupled system with feedbacks that can stabilize habitability, have gained traction and empirical support. Gaia's enduring legacy is not only the debates it sparked but the way it reshaped thinking about Earth as an integrated system. It shifted the conversation from a passive planet hosting life to a dynamic coevolution of biosphere and geosphere, highlighting the deep reciprocity between life and its world. For that reason, Gaia remains both controversial and profoundly influential, a bridge between science, philosophy, and environmental consciousness. Loop quantum gravity. Loop quantum gravity is a theoretical framework that seeks to reconcile the principles of quantum mechanics with general relativity, providing a quantum description of gravity without invoking extra dimensions or hypothetical entities such as strings. It emerges from the recognition that, at extremely small scales, near the Planck length of 10 to the -35 th power meters, the smooth continuum of space and time described by Einstein's equations cannot remain valid. Instead, space and time themselves must exhibit a discrete, quantized structure. Loop quantum gravity, often abbreviated as LQG, attempts to capture this quantum geometry and explain the fabric of spacetime as a network of finite loops rather than a continuous expanse. The foundational idea behind loop quantum gravity is that space is not infinitely divisible. In classical general relativity, spacetime is modeled as a smooth manifold that curves under the influence of mass and energy. However, quantum mechanics suggests that physical quantities come in discrete units, or quanta. Extending this principle to spacetime implies that geometric quantities such as area and volume should also be quantized. Loop quantum gravity formalizes this concept by representing space as a spin network, a web-like structure composed of nodes and links, where each node represents a quantum of volume and each link represents a quantum of area. These networks evolve over time into spin foams, which provide a quantum description of spacetime itself. The result is a picture of the universe where geometry is granular at the smallest scales, and smoothness is an emergent property at large scales. One of the most distinctive aspects of loop quantum gravity is that it takes general relativity as its starting point and applies the principles of quantization directly to the gravitational field, rather than attempting to unify all forces in a single framework, as string theory does. It reformulates Einstein's theory using a mathematical structure known as the Ushteker variables, which recast general relativity into a form more amenable to quantization. This approach preserves background independence, a fundamental feature of relativity, meaning that space is not treated as an inert backdrop but as a dynamic entity that interacts with matter and energy. This contrasts with many quantum field theories, which assume a fixed spacetime background and thus cannot easily accommodate the dynamical nature of gravity. Loop quantum gravity offers several striking implications for the nature of the universe. One of its most significant predictions is that spacetime is discrete at the Planck scale, consisting of finite chunks rather than a continuum. This quantization of geometry has profound consequences for black holes and cosmology. For black holes, LQG provides a natural way to calculate entropy, the measure of microscopic configurations corresponding to a black hole's horizon, by counting the possible states of the spin network that forms the horizon. Remarkably, the result matches the famous Bekenstein-Hawking formula, which associates black hole entropy with the area of its event horizon, lending credibility to the theory. In cosmology, loop quantum gravity leads to the concept of loop quantum cosmology, which applies the principles of LQG to the entire universe. One of its most intriguing predictions is the resolution of the Big Bang singularity. In classical general relativity, tracing the universe backward in time leads to a point of infinite density and curvature, a singularity where the laws of physics break down. LQG modifies this picture by introducing quantum effects that become dominant at extremely high densities. These effects produce a repulsive force that counteracts gravity, preventing the formation of a singularity. Instead of a beginning from nothing, the universe may have undergone a bounce, contracting to a finite minimum volume before expanding again. This Big Bounce scenario replaces the singularity with a cyclic or pre-Big Bang phase, offering a more complete and consistent description of cosmic origins. Despite its conceptual elegance and promising features, loop quantum gravity remains highly speculative and controversial, primarily because it lacks direct experimental confirmation. Testing predictions at the Planck scale is far beyond the capabilities of current technology. However, researchers have proposed possible observational signatures, such as subtle effects on the polarization of the cosmic microwave background, tiny violations of Lorentz invariance, or imprints on the propagation of high-energy particles across vast cosmic distances. So far, no conclusive evidence has been found, leaving the theory in the realm of theoretical exploration. Critics argue that LQG, while mathematically rigorous, does not yet provide a fully developed framework for unifying gravity with the other fundamental forces of nature. Unlike string theory, which aspires to a theory of everything, loop quantum gravity focuses exclusively on quantizing gravity and remains silent on the structure of matter fields and interactions beyond gravity. Some physicists view this as a limitation, while others regard it as a strength, emphasizing that LQG tackles the core problem, quantizing spacetime, without introducing speculative elements like extra dimensions or supersymmetry. Nevertheless, the absence of a clear link to experimental data continues to fuel debate over its viability. Philosophically, loop quantum gravity offers a radically new picture of reality. It implies that space and time are not fundamental, continuous entities but emergent phenomena arising from the interactions of discrete quantum geometries. Time, in particular, becomes a subtle concept, not an absolute parameter but an emergent property linked to change and relational structures. This challenges classical intuitions and aligns with the idea that the universe at its most fundamental level consists of processes and relationships rather than objects in a pre-existing space. In the broader context of theoretical physics, loop quantum gravity stands as a compelling alternative to string theory, driven by different principles and methodologies. While both aim to bridge the gap between quantum mechanics and general relativity, they offer contrasting visions of the universe, one grounded in vibrating strings and extra dimensions, the other in quantized loops of spacetime. Which, if either, of these frameworks ultimately reflects the true nature of reality remains unknown. Yet, in striving to understand the quantum structure of the cosmos, loop quantum gravity continues to push the boundaries of knowledge, revealing the profound mystery and complexity at the heart of existence. Pilot wave theory. Pilot wave theory, also known as Bohmian mechanics, is a deterministic interpretation of quantum mechanics that offers a radically different picture of the microscopic world compared to the dominant Copenhagen interpretation. While standard quantum mechanics embraces inherent randomness in measurement outcomes, pilot wave theory asserts that quantum behavior can be understood in terms of particles following well-defined trajectories under the guidance of an accompanying pilot wave. This interpretation restores classical notions of determinism and realism, ideas largely abandoned by mainstream physics after the advent of quantum mechanics, by positing that uncertainty arises not from indeterminacy in nature but from incomplete knowledge of the underlying variables governing the system. The origins of the pilot wave idea trace back to the work of Louis de Broglie in the 1920s, who introduced the concept of matter waves. De Broglie proposed that every particle, such as an electron, is associated with a wave that determines its motion, much like a pilot directing a ship. This notion was initially presented as part of his doctoral thesis and influenced the development of wave mechanics by Schrödinger. However, de Broglie's interpretation was overshadowed by the rise of the Copenhagen interpretation, which declared that the wave function represented only a probability amplitude, not a physical guiding wave. It was not until the 1950s that David Bohm revived and extended the idea, formulating a complete theory that became known as Bohmian mechanics. In pilot wave theory, the wave function, described mathematically by Schrödinger's equation, is treated as a real physical entity, not merely a tool for predicting probabilities. This wave exists in configuration space and evolves deterministically according to Schrödinger's dynamics. Particles, meanwhile, are not smeared out in space as the Copenhagen interpretation suggests but have definite positions at all times. Their motion is guided by the quantum potential, a non-local potential derived from the wave function. The guiding equation specifies that a particle's velocity depends on the phase of the wave function, so the wave effectively acts like an invisible pilot steering the particle along a trajectory. As a result, what appears to us as quantum randomness is actually the consequence of ignorance about the exact initial conditions of both the particle and the wave. This interpretation provides a strikingly intuitive account of phenomena like interference and diffraction. Consider the famous double-slit experiment. In the standard interpretation, a single electron appears to pass through both slits as a probability wave, then collapses to a point upon detection. In the pilot wave picture, the electron passes through one slit as a localized particle, but the guiding wave passes through both slits and interferes with itself, creating a pattern that influences the particle's trajectory. When many electrons are sent through the apparatus, their individual deterministic paths, guided by the pilot wave, collectively reproduce the interference pattern without invoking wave function collapse or intrinsic randomness. Thus, the probabilistic predictions of standard quantum mechanics emerge as statistical consequences of deterministic laws applied to hidden variables. One of the most distinctive features of Bohmian mechanics is its explicit non-locality. The quantum potential that guides particles depends on the global configuration of the system, meaning that the behavior of one particle can be instantaneously affected by distant conditions if the particles are entangled. This non-local character is not unique to pilot wave theory. Bell's theorem and related experiments have demonstrated that any viable interpretation of quantum mechanics must accommodate non-locality, but Bohmian mechanics makes this feature explicit. In an entangled system, the guiding wave encompasses all particles simultaneously, so the motion of each particle depends on the positions of the others, regardless of the spatial separation between them. This does not allow faster-than-light signaling because the influence is holistic and does not transmit usable information. But it does challenge classical intuitions about locality and separability. Critics of pilot wave theory often point to its reliance on configuration space rather than physical three-dimensional space, raising questions about the ontological status of the guiding wave. If the wave function exists in a high-dimensional space, how can it physically influence particles in ordinary space? Supporters argue that this is no more problematic than other abstract structures in physics and that the theory's internal consistency and explanatory power justify its assumptions. Another challenge lies in reconciling pilot wave theory with relativity. Because the guiding equation introduces a preferred foliation of spacetime to define simultaneity in non-local interactions, the theory does not naturally incorporate Lorentz invariance. Various attempts have been made to construct relativistic versions of Bohmian mechanics, often by introducing additional structures such as preferred frames, but these remain contentious and complex. Despite these difficulties, pilot wave theory has notable strengths. It provides a clear ontology, specifying what exists, particles with definite positions and a guiding wave, and how these entities evolve over time. Unlike the Copenhagen interpretation, it does not require a special role for measurement or consciousness in collapsing the wave function. There is no ambiguity about when or how collapse occurs because, in this framework, there is no collapse at all. Measurements simply reveal pre-existing properties of particles, determined by the guiding wave. This makes the theory conceptually appealing to those who favor a realist and deterministic worldview, even though it departs from certain philosophical preferences in mainstream physics. Experimentally, Bohmian mechanics reproduces all the predictions of standard quantum mechanics for non-relativistic systems, so it cannot be easily falsified by current data. Some researchers have proposed that novel predictions might arise in quantum cosmology, quantum field theory, or experiments involving weak measurements, but so far no empirical result has decisively distinguished it from other interpretations. Its value lies primarily in providing an alternative conceptual framework that resolves certain interpretational puzzles, such as the measurement problem, without invoking multiple universes or abandoning realism. Philosophically, the pilot wave theory occupies an important niche in the landscape of quantum foundations. It demonstrates that the probabilistic nature of quantum mechanics is not inevitable but contingent on interpretive choices. It challenges the orthodoxy of Copenhagen and the extravagance of many worlds by offering a middle path, deterministic, realist, and single world, yet non-local and deeply counterintuitive. For these reasons, Bohmian mechanics remains both controversial and influential, serving as a reminder that quantum mechanics, even a century after its birth, has not surrendered all its mysteries, and that alternative visions of reality, grounded in rigorous mathematics, continue to shape the debate about what the theory truly means. Plasma cosmology. Plasma cosmology is an alternative and highly controversial model of the universe that emphasizes the role of plasma, the fourth state of matter, consisting of charged particles, in shaping cosmic structures and dynamics. Unlike the standard cosmological model, which is built upon the framework of general relativity and the Big Bang theory, plasma cosmology posits that electromagnetic forces, rather than gravity alone, play a dominant role in organizing matter at large scales. This approach emerges from the recognition that more than 99% of visible matter in the universe exists in the plasma state, from stars and interstellar gas to intergalactic media, and that plasma behavior is governed by complex electromagnetic interactions that can far outweigh gravitational effects in certain contexts. The roots of plasma cosmology can be traced back to the mid-20th century and the work of scientists such as Hannes Alfvén, a Nobel laureate in physics who pioneered plasma physics and magnetohydrodynamics. Alfvén and his followers argued that cosmology should account for the known properties of plasma and electromagnetic forces, which are enormously stronger than gravity at the scale of individual particles. While gravity is the weakest of the fundamental forces, its cumulative effect dominates at large scales because it is always attractive and acts over infinite distances. However, plasma cosmologists claim that electromagnetic effects, arising from the motion of charged particles and the presence of cosmic magnetic fields, cannot be neglected and may actually govern the formation of cosmic structures such as galaxies, clusters, and filaments. In contrast to the Big Bang model, which envisions a universe originating from a singularity and expanding over billions of years, plasma cosmology traditionally supports a steady-state or quasi-steady-state universe with no definite beginning or end. According to this view, matter and energy are continuously redistributed by vast electrical currents and magnetic fields on cosmic scales. The universe, in this picture, is not driven primarily by gravitational collapse and dark energy, but by the interaction of electrically charged matter in gigantic plasma structures. Plasma cosmologists argue that observed phenomena such as galaxy rotation curves, large-scale filamentary structures, and high-energy cosmic jets can be explained by plasma behavior without invoking dark matter or dark energy, which they regard as hypothetical constructs introduced to patch inconsistencies in the gravitational model. One of the key concepts in plasma cosmology is the idea of Birkeland currents, vast, filamentary currents of charged particles flowing through space, named after Christian Birkeland, who first studied auroral phenomena and proposed electrical currents in the Earth's magnetosphere. Plasma cosmologists extend this idea to intergalactic scales, suggesting that Birkeland currents weave the cosmic web, channeling matter into filaments and nodes where galaxies form. These currents generate enormous magnetic fields, which in turn influence the motion of matter and the morphology of cosmic structures. This explanation contrasts with the Standard Model, which attributes the cosmic web primarily to gravitational amplification of initial density fluctuations in the early universe. Supporters of plasma cosmology point to several observational features that they claim are more naturally explained by electromagnetic processes than by purely gravitational models. For instance, the filamentary nature of the cosmic web, the alignment of galactic magnetic fields, and the existence of powerful astrophysical jets emanating from active galactic nuclei are cited as evidence of large-scale plasma interactions. They argue that conventional cosmology underestimates the significance of magnetism and electric currents in shaping these phenomena, often treating them as secondary effects rather than primary drivers. However, plasma cosmology is not without its profound difficulties and criticisms. The most significant challenge is its incompatibility with the overwhelming body of evidence supporting the Big Bang model. Observations such as the cosmic microwave background radiation, CMB, the abundance of light elements predicted by Big Bang nucleosynthesis, and the large-scale expansion of the universe measured by redshift surveys strongly favor a hot Big Bang origin. Plasma cosmologists have attempted to reinterpret these observations, suggesting that the CMB could arise from starlight scattered by intergalactic plasma rather than being a relic of an early hot phase, but such explanations have not matched the precision and consistency of the Standard Model. Similarly, plasma cosmology struggles to account for the observed distribution of elements without invoking processes analogous to Big Bang nucleosynthesis. Another major obstacle is that the electromagnetic forces emphasized by plasma cosmology tend to cancel out over large scales because positive and negative charges balance each other, leaving gravity as the dominant long-range force. While localized regions of plasma can exhibit strong electromagnetic interactions, critics argue that these effects cannot replace gravity as the primary organizing force of the universe on cosmological scales. Furthermore, the predictive power of plasma cosmology has not matched that of the lambda-CDM model, which successfully accounts for a wide range of observational data, including the precise fluctuations in the CMB and the accelerating expansion of the universe. Despite its marginal status in mainstream cosmology, plasma cosmology remains intellectually provocative because it challenges the assumption that gravity alone governs cosmic evolution. It underscores the fact that the universe is pervaded by plasma and threaded with magnetic fields, and it pushes theorists to consider the role of electromagnetism more seriously in astrophysical processes. Some aspects of plasma physics have indeed been integrated into modern astrophysics, particularly in the study of star formation, galactic dynamics, and high-energy phenomena. However, the grand vision of plasma cosmology, a universe without a Big Bang, structured primarily by electrical forces, remains largely rejected by the scientific community. At a deeper philosophical level, plasma cosmology illustrates the tension between elegant theoretical models and the messy reality of observational evidence. Its proponents argue that the standard cosmological model has become increasingly reliant on unobservable entities, such as dark matter and dark energy, whereas plasma cosmology seeks explanations rooted in well-understood physical principles. Critics counter that these new components are not ad hoc but are required to explain a wide range of data, whereas plasma cosmology fails to offer a coherent framework of comparable explanatory power. The debate, while far from settled in the minds of its advocates, highlights the dynamic and sometimes contentious nature of scientific progress, where even controversial ideas can serve as a catalyst for deeper inquiry. Quantum biology. Quantum biology is a field that sits at the intersection of physics and biology, and it has provoked considerable controversy because it suggests that some of life's most fundamental processes may rely on principles usually confined to the microscopic world of quantum mechanics. For much of the 20th century, biology was thought to operate firmly in the realm of classical physics and chemistry. DNA, proteins, cells, and tissues followed deterministic rules that could be explained by molecular interactions and thermodynamics. Quantum mechanics, with its counterintuitive phenomena of superposition, tunneling, and entanglement, was seen as largely irrelevant to the warm, noisy, and wet environments of living systems, conditions under which fragile quantum effects should collapse almost instantly. Yet, over the last few decades, evidence has emerged that certain biological processes may indeed exploit quantum phenomena, challenging the neat boundary between physics and biology and opening up one of the most intriguing and controversial frontiers in science. The central claim of quantum biology is that organisms have evolved mechanisms to harness quantum effects in ways that enhance efficiency or enable processes that would otherwise be impossible. A well-studied example is photosynthesis. In plants, algae, and photosynthetic bacteria, the capture of light energy is astonishingly efficient, with energy transfer to reaction centers occurring with nearly perfect fidelity. Experiments using ultrafast spectroscopy have suggested that this efficiency might be explained by quantum coherence, a state in which energy exists in multiple pathways simultaneously, allowing the system to sample various routes and select the most efficient one. Instead of energy moving step by step in a classical manner, quantum superposition allows it to explore all possible paths at once, collapsing into the optimal route. This finding suggests that photosynthetic organisms may have evolved to preserve delicate quantum states long enough to confer a biological advantage. Another area where quantum biology has gained attention is in the navigation of migratory birds. Many bird species are able to traverse thousands of kilometers with uncanny precision, and one hypothesis is that they use the Earth's magnetic field as a guide. But how can biological molecules sense such a weak force? The leading model involves a quantum mechanism called the radical pair hypothesis. In this process, light excites certain proteins in the bird's eye, producing paired electrons whose spins are quantum mechanically entangled. The alignment of these spins is sensitive to the Earth's magnetic field, potentially influencing chemical reactions in a way that provides the bird with a biological compass. If true, this would mean that migratory navigation depends directly on quantum entanglement, a phenomenon often associated with laboratory physics experiments rather than living organisms. Quantum tunneling, another strange quantum effect, has also been implicated in biology. Tunneling allows particles such as electrons or protons to pass through energy barriers that would be insurmountable under classical physics. In enzymes, tunneling may explain how reactions occur at rates far faster than would otherwise be expected. Some studies suggest that protons tunnel across hydrogen bonds in DNA, possibly leading to mutations during replication. If proton tunneling can alter base pairing, it might even play a role in genetic variation and evolution. Similarly, in olfaction, one controversial theory proposes that humans and animals may detect smells not by the shape of molecules alone, the traditional lock and key model, but by sensing vibrational frequencies of molecules through inelastic electron tunneling. This quantum smell hypothesis remains debated, but it illustrates the wide-ranging implications of quantum biology. What makes quantum biology controversial is not only the extraordinary claims but also the extraordinary evidence required to support them. Quantum phenomena are notoriously delicate, easily destroyed by interactions with the environment in a process called decoherence. In the messy, thermal environments of living cells, decoherence should occur almost instantly, preventing sustained quantum effects. Yet, if life does exploit quantum mechanics, it implies that organisms have evolved structures that shield quantum states or even exploit decoherence itself in productive ways. This would represent a form of biological engineering that is far more subtle and sophisticated than previously imagined. Skeptics argue that while quantum effects are inevitable at the molecular scale, since all matter ultimately follows quantum laws, this does not mean they are biologically significant. They may exist, but only as background phenomena, with no functional role in shaping life processes. From this perspective, invoking quantum biology risks overstating the case, attributing evolutionary outcomes to exotic physics when simpler biochemical explanations may suffice. Critics caution that the field, because of its novelty and its resonance with the mystique of quantum mechanics, sometimes attracts speculative ideas that outpace experimental validation. Proponents counter that dismissing quantum biology too quickly ignores mounting experimental evidence and the possibility that evolution has harnessed quantum effects in ways we are only beginning to grasp. They point out that photosynthetic quantum coherence has been replicated across multiple organisms and experimental setups, and that the radical pair mechanism in birds is supported by both behavioral studies and biophysical models. Even if some claims turn out to be exaggerated, they argue, quantum biology is likely to reveal unexpected dimensions of how life operates. Beyond the scientific debate, quantum biology raises philosophical questions about the nature of life itself. If living systems are not only chemical but also quantum mechanical, then biology is deeply entwined with the fundamental physics of the universe. This perspective could reshape our understanding of consciousness, evolution, and the boundary between the living and the non-living. Some researchers have speculated, though controversially, that quantum effects might even underlie brain function or consciousness, though such claims remain highly speculative and largely unsupported. In summary, quantum biology explores the possibility that living systems harness the strange properties of quantum mechanics to perform functions that classical biology cannot fully explain. It has produced tantalizing evidence in photosynthesis, magnetoreception, enzyme catalysis, DNA stability, and perhaps even smell. Yet the field remains controversial, with many scientists urging caution until more rigorous proof is available. Whether quantum biology turns out to be a revolution in our understanding of life or a collection of intriguing but limited exceptions, it has already expanded the conversation, forcing biologists and physicists alike to rethink the boundaries between their disciplines and to consider the possibility that life is, in part, written in the language of the quantum world. Abiogenic petroleum origin. The abiogenic petroleum origin hypothesis is a controversial idea that challenges the widely accepted notion that petroleum and natural gas are formed primarily from the decomposition of ancient biological material buried deep within the Earth. In contrast to the conventional biogenic model, which attributes hydrocarbon formation to the transformation of organic matter, mostly microscopic marine organisms and plant material, under high pressure and temperature over millions of years, the abiogenic hypothesis proposes that significant quantities of hydrocarbons originate from non-biological processes deep in the Earth's mantle or crust. According to this view, petroleum is not the fossilized residue of life but rather a primordial substance generated by geochemical and thermodynamic processes that occur independently of biological activity. The fundamental basis of the abiogenic theory lies in the observation that hydrocarbons are not rare in the universe. They are found on planets and moons that have never hosted life, such as Titan, Saturn's largest moon, which has methane lakes and a thick hydrocarbon-rich atmosphere. Comets and interstellar clouds contain complex organic molecules, and some meteorites carry hydrocarbons as well. These extraterrestrial occurrences strongly suggest that hydrocarbons can form without any involvement of life, under purely chemical and physical conditions. Advocates of the abiogenic theory argue that if hydrocarbons can form in space, they could also form naturally in the Earth's interior under high pressures and temperatures where carbon and hydrogen are abundant. The most commonly cited mechanism for abiogenic hydrocarbon formation is the reduction of carbon compounds deep in the mantle. The Earth formed from primordial material that included metallic iron and compounds of carbon and oxygen. Under the high pressures and temperatures present in the mantle, chemical equilibria may favor the synthesis of hydrocarbons from simpler carbon species like carbon dioxide or carbon monoxide in the presence of hydrogen. For example, a reaction involving iron oxides and water can produce hydrogen, which then reacts with carbon-bearing species to form methane and heavier hydrocarbons. This process can be modeled thermodynamically and experimentally, and some laboratory experiments at pressures exceeding 30 kilobars and temperatures of 1000 degrees Celsius or higher have successfully synthesized methane and even more complex hydrocarbons from carbonate or graphite sources under mantle-like conditions. Supporters of the abiogenic theory argue that the Earth's deep interior contains significant amounts of carbon locked in minerals and fluids. If this carbon interacts with hydrogen derived from water, hydrocarbons could be generated continuously at depth and migrate upward through fractures, faults, and porous rocks until they accumulate in reservoirs in the crust. This concept implies that petroleum may not be a finite resource derived from biological remains, but rather a dynamically replenished material, a suggestion that, if true, would have profound economic and geopolitical implications. Historically, the idea of abiogenic petroleum origins dates back to the 19th century, when scientists like Dmitry Mendeleev speculated that iron carbide reacting with water in the Earth's interior could produce hydrocarbons. In the 20th century, Soviet and Ukrainian geologists, most notably Nikolai Kudryavtsev, advanced a more rigorous form of the theory, supported by experiments and observations. They argued that many large oil and gas fields occur in crystalline basement rocks rather than in sedimentary basins, which is difficult to explain by purely biogenic models. These fields, often associated with deep faults and tectonic fractures, were interpreted as evidence for hydrocarbon migration from deep within the Earth. Proponents also point to the discovery of hydrocarbons in igneous and metamorphic rocks, the presence of methane in volcanic gases, and the detection of hydrocarbons in mantle-derived inclusions in diamonds and deep-seated rocks as circumstantial evidence for abiogenic processes. Additionally, the existence of massive methane reservoirs on other planetary bodies reinforces the plausibility of non-biological hydrocarbon synthesis under natural conditions. However, the abiogenic hypothesis faces strong criticism and remains a minority position in the scientific community. The primary counterargument is that the overwhelming majority of observed petroleum deposits exhibit geochemical signatures that are clearly linked to biological precursors. Crude oil typically contains biomarkers, complex organic molecules such as porphyrins, steranes, and hopanes, that are derived from the remains of ancient living organisms. These compounds are structurally related to chlorophyll, cell membranes, and other biological components, and their presence in petroleum is difficult to reconcile with a purely abiogenic origin. Furthermore, the isotopic composition of carbon in petroleum generally shows a preference for lighter carbon isotopes, a hallmark of biological fractionation, which is consistent with organic origin. Another challenge for the abiogenic theory is explaining the spatial distribution and association of oil and gas with sedimentary basins. Most commercial petroleum accumulations are found in sedimentary rocks where organic matter was deposited and buried. These rocks show clear evidence of source material, maturation pathways, and migration processes that fit the conventional biogenic model. While hydrocarbons do occur in crystalline basement rocks, these are usually explained as secondary accumulations that migrated from overlying sedimentary layers rather than primary abiogenic sources. In addition, modern exploration and production strategies based on biogenic principles have been remarkably successful in predicting and locating hydrocarbon reserves, whereas abiogenic models have not produced equivalent predictive power. Nevertheless, there is a middle ground. Even within the mainstream geoscience community, it is acknowledged that small amounts of hydrocarbons, particularly methane, are generated by abiotic processes in certain geological environments. For example, serpentinization, a chemical reaction between water and ultramafic rocks in the mantle and lower crust, produces hydrogen, which can then react with carbon dioxide to form methane. This mechanism is invoked to explain methane in hydrothermal vent systems on the ocean floor and possibly on other planetary bodies. However, these processes likely contribute only a minor fraction of Earth's petroleum resources compared to those formed biologically. In summary, the abiogenic petroleum origin hypothesis remains an intriguing and controversial alternative to the conventional biogenic theory. It draws strength from cosmochemical evidence, high-pressure experiments, and the existence of hydrocarbons in deep Earth and extraterrestrial environments. Yet, the weight of geochemical, isotopic, and geological evidence strongly supports a biological origin for the vast majority of the world's petroleum deposits. While abiotic processes undoubtedly produce some hydrocarbons and may even contribute to certain deep reservoirs, they do not appear to be the primary mechanism responsible for the enormous oil and gas accumulations exploited by humanity. The debate, however, continues to stimulate research into deep Earth processes, the distribution of carbon within the planet, and the chemical possibilities of life-independent organic synthesis. Anthropic Principle. The Anthropic Principle is a philosophical and scientific concept that seeks to explain why the physical constants and conditions of the universe appear to be finely tuned for the existence of life, particularly intelligent observers like ourselves. At its core, the principle suggests that the universe must have properties that allow life to exist, because if it did not, we would not be here to observe it. This reasoning, while seemingly tautological at first glance, has profound implications for cosmology, physics, and our understanding of reality. It raises questions about whether the universe's apparent fine-tuning is a coincidence, a necessity, or evidence of deeper principles at work. The origin of the anthropic principle lies in the observation that the fundamental constants of nature, the gravitational constant, the strength of the electromagnetic force, the masses of elementary particles, the ratio of dark energy to matter, and many others, fall within very narrow ranges that permit the emergence of stars, planets, complex chemistry, and ultimately life. If any of these constants were slightly different, the universe as we know it could not exist. For example, if the strong nuclear force were marginally weaker, atomic nuclei would not hold together, and no complex matter would form. If it were slightly stronger, all hydrogen would fuse rapidly into heavier elements, leaving no fuel for long-lived stars like the Sun. Similarly, if the cosmological constant, the energy density of empty space, were much larger than its observed value, the universe would have expanded so rapidly after the Big Bang that galaxies and stars could never have formed. These examples illustrate the extraordinary degree of fine-tuning apparent in the cosmos. The anthropic principle comes in two primary forms, the weak anthropic principle and the strong anthropic principle. The weak version states that the observed values of the physical and cosmological constants are conditioned by the requirement that they allow the existence of observers. In other words, we should not be surprised to find ourselves in a universe that permits life because only such a universe could contain observers. This form of the principle is often regarded as a selection effect rather than an explanatory mechanism. It does not claim to explain why the constants have their particular values, only why we observe them as they are. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to exist, either as a fundamental feature of physical law or as an outcome of deeper principles. This interpretation has been criticized for bordering on teleology, as it seems to imply that the universe is in some sense designed or compelled to produce life. The anthropic principle gained renewed attention in modern cosmology because of discoveries related to cosmic inflation, dark energy, and the apparent flatness of the universe. These features, combined with the improbably small value of the cosmological constant, have made fine-tuning a central puzzle in theoretical physics. Some physicists invoke the anthropic principle in conjunction with the multiverse hypothesis, arguing that if there exists an enormous number of universes with varying physical constants, then it is unsurprising that we find ourselves in one where conditions happen to allow life. In this view, fine-tuning does not require an underlying physical necessity or a designer, it is simply a statistical inevitability in a vast ensemble of universes. This explanation, however, depends on the unproven assumption that a multiverse exists, making it controversial. Critics of the anthropic principle argue that it is not a scientific explanation because it lacks predictive power and cannot be tested directly. They contend that invoking the anthropic principle amounts to giving up on finding a deeper physical reason for the observed constants, replacing scientific inquiry with a philosophical assertion. Others counter that it provides a useful heuristic by reminding us that any theory of fundamental physics must be consistent with the existence of observers and that selection effects cannot be ignored when interpreting cosmological data. In this sense, the principle operates as a constraint on scientific theories rather than a mechanism of causation. The Anthropic Principle also intersects with philosophical and theological debates. Its suggestion that the universe is finely tuned for life has been interpreted by some as evidence of purpose or design, while others view the multiverse explanation as an attempt to eliminate any appearance of design by appealing to chance on a grand scale. These interpretations highlight the principle's controversial nature, as it straddles the boundary between empirical science and metaphysical speculation. Despite the debates surrounding it, the Anthropic Principle has influenced discussions in fundamental physics, particularly in the context of string theory and the string landscape. With an estimated 10 to the power of 500 possible solutions corresponding to different sets of physical constants, string theory offers no unique prediction for the observed values. In this framework, the Anthropic Principle is sometimes invoked to explain why we observe a universe compatible with life, as only such regions of the landscape can harbor observers. Whether this constitutes an explanation or a statement of inevitability remains a matter of contention. In the end, the Anthropic Principle challenges us to consider the interplay between observation and reality. It forces us to ask whether the universe is uniquely suited for life by necessity, by chance, or by something deeper we do not yet understand. While it may never yield a definitive answer, the principle serves as a lens through which the profound mystery of existence becomes even more apparent, compelling us to explore the limits of science, philosophy, and imagination in our quest to understand why the universe is the way it is. Climate engineering. Climate engineering, often called geoengineering, is a controversial and highly debated field of science and policy that proposes the deliberate, large-scale intervention in Earth's climate system to counteract or mitigate the effects of global warming. Unlike conventional climate strategies, which focus on reducing greenhouse gas emissions or adapting to their impacts, climate engineering aims to directly alter planetary systems, whether by reflecting sunlight, removing carbon dioxide from the atmosphere, or modifying ecosystems, to artificially control Earth's temperature. It straddles the boundary between scientific ingenuity and ethical dilemma, raising questions not only about feasibility and effectiveness but also about governance, unintended consequences, and humanity's role in reshaping the planet. The idea arises from the growing recognition that efforts to reduce greenhouse gas emissions may not be enough to prevent dangerous climate change. Carbon dioxide levels continue to climb, global average temperatures are rising, and extreme weather events are becoming more frequent. Against this backdrop, geoengineering is often framed as a Plan B, a last resort set of tools to stabilize the climate if mitigation and adaptation prove insufficient. Yet the very notion of intentionally manipulating the Earth's atmosphere and oceans unsettles many scientists, ethicists, and policymakers, who see it as both risky and a potential moral hazard, possibly undermining the political will to reduce emissions in the first place. Climate engineering is generally divided into two broad categories: solar radiation management, SRM, and carbon dioxide removal, CDR. Solar radiation management seeks to reduce the amount of sunlight reaching the Earth's surface, thereby cooling the planet. Proposals include injecting reflective aerosols, such as sulfur dioxide, into the stratosphere to mimic the cooling effect of volcanic eruptions, or deploying vast fleets of reflective mirrors in space. Other ideas involve brightening marine clouds by spraying seawater droplets into the atmosphere or increasing the reflectivity of Earth's surface through changes in land use, such as painting rooftops white or cultivating reflective crops. SRM could, in principle, produce a rapid cooling effect at relatively low cost, but it does not address the underlying problem of excess greenhouse gases, nor does it solve issues such as ocean acidification. Moreover, SRM carries the risk of severe unintended consequences, including disruption of rainfall patterns, shifts in monsoon systems, and uneven regional impacts, where some areas might benefit while others suffer. Carbon dioxide removal, by contrast, aims to tackle the root cause of climate change by reducing the concentration of greenhouse gases in the atmosphere. Proposals range from natural approaches, such as large-scale afforestation and reforestation, to high-tech methods like direct air capture machines that chemically filter CO2 from the air and store it underground. Other CDR concepts include ocean fertilization, where nutrients such as iron are added to stimulate plankton growth, thereby enhancing CO2 absorption, or the use of bioenergy with carbon capture and storage, BECCS, which combines biomass energy production with CO2 sequestration. Unlike SRM, CDR addresses the long-term buildup of greenhouse gases, but it is generally slower to produce cooling effects and requires massive infrastructure and land use, potentially competing with agriculture or biodiversity. The controversies surrounding climate engineering are as much ethical and political as they are scientific. A central concern is the problem of governance: who decides when, how, and whether to deploy such technologies. Because the climate system is shared by all nations, unilateral action by one country could have global consequences, sparking geopolitical tensions. For instance, a nation suffering from drought might accuse another of using geoengineering to shift rainfall patterns in its own favor. This creates the potential for climate interventions to become tools of conflict or coercion rather than cooperation. Another concern is the uncertainty of unintended consequences. Earth's climate system is enormously complex, and interventions at a planetary scale carry risks of unpredictable and possibly irreversible changes. While computer models can simulate outcomes, real-world experiments would necessarily involve interfering with delicate systems on which billions of people and ecosystems depend. Critics argue that the possibility of catastrophic side effects makes large-scale deployment reckless. Advocates respond that small-scale research, carefully regulated, is essential to understand risks and prepare for scenarios where climate engineering might be the only viable option. There is also the ethical problem of the moral hazard. Some fear that the promise of geoengineering could reduce the urgency of cutting emissions, encouraging policymakers and industries to delay hard choices in favor of speculative technological fixes. If societies become reliant on geoengineering while continuing to emit greenhouse gases, the world might face a situation of climate lock-in, where constant technological intervention is needed to keep temperatures stable. Stopping suddenly could lead to a rapid rebound of warming, with devastating consequences. Despite the risks, some scientists argue that climate engineering deserves serious consideration, precisely because the stakes of inaction are so high. If global warming continues unchecked, tipping points such as the collapse of ice sheets, dieback of rainforests, or massive release of methane from permafrost could trigger irreversible changes. In such scenarios, geoengineering may represent the only way to buy time for humanity to reduce emissions and transition to sustainable systems. Thus, research into climate engineering is often framed not as advocacy for deployment, but as a precautionary measure to ensure society understands the tools available if crisis demands them. The debate over climate engineering therefore reflects broader questions about humanity's relationship with the planet. Are we stewards capable of responsibly managing Earth's climate, or would attempts to do so be hubristic overreach with catastrophic consequences? Is the greater moral failing to risk dangerous interventions, or to refuse to explore them in the face of escalating climate threats? These questions ensure that climate engineering remains not only a scientific controversy but also a philosophical and political one. In summary, climate engineering is a contested and provocative theory that suggests deliberate manipulation of Earth systems as a response to climate change. It offers both a promise of planetary rescue and the peril of planetary disruption. Advocates see it as an emergency tool, critics as an irresponsible gamble, and nearly everyone agrees that its governance, ethics, and consequences are fraught with uncertainty. Whether it becomes a real part of humanity's future or remains a speculative concept, the very debate reflects the profound dilemma of living in an era where human activity has become a force capable of reshaping the entire Earth system. Epigenetics versus Neo-Darwinism. The debate between epigenetics and Neo-Darwinism touches some of the deepest questions about how evolution works and how biological traits are inherited across generations. At its center lies a controversy over whether the modern evolutionary synthesis, often called Neo-Darwinism, which combines Darwin's theory of natural selection with Mendelian genetics, fully captures the mechanisms of heredity and variation, or whether recent discoveries in epigenetics demand a significant revision of evolutionary theory. Neo-Darwinism, which emerged in the mid-20th century, unified the idea that natural selection acts on heritable variation with the understanding that genes, composed of DNA, are the fundamental units of heredity. According to this view, random mutations in DNA produce variation. Natural selection favors those variants that enhance survival and reproduction, and over many generations, this process explains adaptation and the diversity of life. Importantly, the Neo-Darwinian framework assumes that the genetic sequence itself is the primary and stable substrate of inheritance. Changes in traits that are not encoded in DNA are typically transient and do not contribute to long-term evolutionary change. Epigenetics complicates this picture. The term refers to heritable changes in gene expression that do not involve alterations in the DNA sequence itself. These changes are mediated by chemical modifications to DNA, such as methylation, modifications to histone proteins around which DNA is wrapped, and non-coding RNAs that regulate gene activity. Epigenetic modifications can switch genes on or off, influence developmental pathways, and shape phenotypes in ways that are responsive to environmental conditions. Crucially, some of these changes can be transmitted from one generation to the next, at least for a limited number of generations, without altering the underlying DNA code. The controversial point arises when epigenetics is interpreted as a modern form of Lamarckism, the idea that traits acquired during an organism's lifetime can be inherited by its offspring. For much of the 20th century, this notion was considered discredited, since Darwinian natural selection operating on random mutations in DNA provided a sufficient and experimentally supported mechanism for evolution. But findings in epigenetics have shown that environmental factors, diet, stress, toxins, social behavior, can induce epigenetic changes that persist into subsequent generations. For example, studies in rodents have demonstrated that exposure to certain chemicals or early life stress can alter methylation patterns in germline cells, with measurable effects on offspring behavior or metabolism. Similar, though more limited, evidence exists in plants, where epigenetic inheritance appears to play a significant role in adaptation to environmental stress. Supporters of an extended evolutionary synthesis argue that these findings undermine the strict Neo-Darwinian view that genetic mutations alone are the raw material of evolution. They contend that epigenetic inheritance represents an additional channel through which variation can be generated and transmitted, one that is not purely random but often responsive to the environment. This opens the door to a kind of environmentally induced, directed variation, a mechanism that seems closer to Lamarck's idea of the inheritance of acquired characteristics than to Darwin's reliance on random mutation. In this view, epigenetics complements natural selection by providing organisms with more flexible, rapid ways of adapting to their environment, and in some cases these adaptations may persist long enough to influence evolutionary trajectories. Critics, however, caution against overstating the evolutionary importance of epigenetics. They argue that while epigenetic modifications are real and biologically significant, most of them are short-lived, typically persisting for only a few generations before being reset. The germline, especially in mammals, undergoes extensive reprogramming during reproduction, which erases most epigenetic marks. Therefore, although epigenetic inheritance may play a role in short-term adaptation or developmental plasticity, its long-term contribution to evolution is likely marginal compared to changes in DNA sequence. Moreover, many supposed examples of transgenerational epigenetic inheritance are difficult to reproduce or disentangle from other factors, such as parental behavior, maternal effects, or ecological inheritance. At the philosophical level, The epigenetics versus Neo-Darwinism debate raises the question of whether evolutionary theory should be expanded to include a broader set of mechanisms beyond genetic mutation and selection. Proponents of the extended synthesis argue that evolution is not just about genes but about multiple interacting systems of inheritance: genetic, epigenetic, behavioral, ecological, and cultural. They emphasize concepts like developmental plasticity, niche construction, and the ability of organisms to shape their environments, all of which complicate the gene-centered view of evolution. Opponents, however, suggest that the existing framework of the modern synthesis is already flexible enough to incorporate these phenomena without requiring a fundamental overhaul. What makes the debate especially contentious is its resonance with older historical disputes. Darwin himself recognized that inheritance was not fully understood in his time, and Lamarck's earlier ideas of acquired characteristics persisted as a rival explanation. When molecular genetics established DNA as the hereditary molecule, it seemed to vindicate the neo-Darwinian picture and banish Lamarckism as a discredited relic. The rise of epigenetics reopens, at least rhetorically, that older conflict, suggesting that Lamarck was not entirely wrong after all. This historical echo gives the controversy symbolic weight beyond the technical details. In practical terms, the study of epigenetics has already reshaped biology. It has illuminated how identical genomes can produce vastly different cell types in development, how environmental stress influences health, and how diseases such as cancer involve widespread epigenetic dysregulation. In agriculture and ecology, epigenetic variation is increasingly recognized as a factor in plant resilience. The question is whether these effects, impressive as they are, extend to the kind of long-term, large-scale evolutionary change that explains biodiversity. In summary, the debate between epigenetics and neo-Darwinism is not simply about data but about the conceptual boundaries of evolutionary theory. Neo-Darwinism holds that DNA mutations filtered by natural selection are the foundation of evolution. Epigenetics shows that heritable, non-genetic changes also play a role, sometimes in ways that appear environmentally responsive. The controversy arises from how much weight one gives to this role. Is epigenetics a supplementary layer within the existing framework, or does it signal the need for a broader evolutionary synthesis that goes beyond the gene-centered paradigm? While the evidence is still being sorted, the discussion itself reflects the dynamism of biology, a field where new discoveries can reopen old debates and force us to reconsider what it means for life to change, adapt, and endure across generations. Hologenome Theory. The hologenome theory of evolution is a relatively recent and controversial idea that challenges the traditional, gene-centered view of evolutionary biology. It suggests that the unit of natural selection is not just the individual organism and its genome, but the host organism together with all of its associated microorganisms and their collective genomes, a system collectively known as the hologenome. In this view, every multicellular organism is not a single, autonomous being, but rather a holobionт, a complex assemblage of the host plus its symbiotic bacteria, viruses, fungi, and other microbes. The hologenome, the sum of genetic information from both the host and its microbiome, becomes the substrate upon which evolution operates. The roots of the theory lie in growing recognition of the microbiome's crucial role in shaping the biology of plants and animals. Over the last few decades, advances in sequencing technologies revealed that all multicellular organisms harbor vast communities of microorganisms that influence digestion, immunity, development, and even behavior. For example, humans carry trillions of microbes in their gut, with microbial genes vastly outnumbering human genes. Similar microbial partnerships exist in corals, insects, and plants, often providing essential functions that the host genome alone cannot accomplish. The hologenome theory formalizes this dependency into an evolutionary framework, proposing that the combined host microbe system should be treated as a single entity subject to selection. One of the most striking implications of this theory is that microbial communities provide a source of heritable variation far beyond what is contained in the host's own DNA. Traditional Neo-Darwinism holds that variation arises primarily from random mutations in the host genome, with natural selection acting on these mutations. The hologenome model suggests an additional, more flexible mechanism. Shifts in the composition of microbial communities can rapidly alter the holobionts' traits. For instance, if environmental changes favor certain microbes that enhance host survival, these microbes may proliferate, effectively altering the holobionts' phenotype. Because microbes are passed vertically, from parent to offspring, or horizontally, acquired from the environment, their contribution can be heritable in a broad sense. This means that evolutionary adaptation can occur not only through slow genetic mutation but also through relatively rapid microbial turnover. Consider the example of corals, often cited in support of the theory. Coral reefs depend on symbiotic algae that live within coral tissues. These algae supply nutrients through photosynthesis, while the coral provides shelter and resources. When ocean temperatures rise, corals may lose their algae in a process called bleaching. However, some corals can recover by forming partnerships with more heat-tolerant algal species, effectively acquiring resilience not through genetic change in the coral itself but through modification of its microbiome. Advocates of the hologenome theory argue that this flexibility exemplifies how selection can act on the holobiont as a whole, with the hologenome providing a dynamic reservoir of adaptive potential. The theory also resonates with broader biological concepts like symbiogenesis, the idea that new species and traits can arise through long-term integration of symbionts. The origin of mitochondria and chloroplasts in eukaryotic cells, once free-living bacteria that became permanent organelles, is a well-accepted example of this principle. The hologenome framework generalizes this logic, suggesting that symbiosis is not an exception but a pervasive driver of evolutionary change. Despite its appeal, the hologenome theory is highly controversial. Critics argue that while microbial communities undeniably influence host biology, they do not meet the criteria for evolutionary units in the same way genes or organisms do. Microbial populations associated with hosts are often unstable, influenced by diet, environment, and chance, making it difficult to define a consistent, heritable hologenome. If the composition of the microbiome can change drastically from one generation to the next, then its role in evolution may be more ecological than genetic. Opponents of the theory therefore prefer to see microbiomes as part of the host's environment, not part of its hereditary identity. Another challenge lies in distinguishing between correlation and causation. For example, the fact that certain microbes are associated with healthier or more resilient hosts does not necessarily mean those microbes are under selective pressure at the level of the holobiont. Microbes evolve on their own timescales and under their own selection pressures, which may or may not align with host fitness. A bacterium that proliferates in the gut may benefit itself without enhancing the survival of the host, raising questions about whether selection truly operates on the holobiont as a cohesive unit. Proponents counter that host and microbes are often so tightly integrated that they cannot be meaningfully separated. Transmission of microbiomes, while imperfect, is often structured. For example, maternal inheritance of microbes during birth or social transfer of microbes in animal groups ensures continuity. Moreover, they argue that even if microbial communities are fluid, this very fluidity provides evolutionary flexibility that rigid genomes cannot offer. By allowing hosts to adapt through microbial reshuffling, the hologenome could be a powerful complement to traditional genetic mechanisms. Philosophically, the debate touches on the very definition of individuality in biology. If organisms are inseparable from their symbionts, then individuality may not reside in a single genome but in an interdependent network of genomes. This perspective challenges the gene-centered view of life and blurs the boundary between organism and environment. It suggests that the evolutionary unit is not an isolated self but a collaborative assemblage, constantly negotiating between stability and change. In summary, The hologenome theory of evolution proposes that the host and its symbiotic microbes form a single evolutionary entity, with the combined hologenome serving as the target of natural selection. It emphasizes the role of microbial variation and symbiosis as engines of adaptability and evolution, potentially expanding the scope of the modern synthesis. However, it remains controversial, with critics questioning the stability, heritability, and coherence of microbiomes as evolutionary units. Whether ultimately validated or not, the theory has already reshaped discussions about individuality, heredity, and the mechanisms of adaptation, highlighting the profound influence of microbes in the story of life. Holographic Principle. The holographic principle is a bold and profound concept in theoretical physics that proposes a radical way of understanding the nature of space, information, and reality itself. At its heart, the principle suggests that all the information contained within a region of space can be fully described by data encoded on the boundary of that region. In other words, the three-dimensional reality we experience may not be fundamental but rather an emergent projection from a two-dimensional surface, much like a hologram, where a flat image can create the illusion of depth. This idea challenges our intuitive notion of the universe as something inherently three-dimensional and instead points to a reality where the fundamental description of nature is lower-dimensional. The origins of the holographic principle lie in attempts to resolve paradoxes associated with black holes. According to general relativity, when matter falls into a black hole, it becomes trapped behind the event horizon, a surface beyond which nothing, not even light, can escape. Classical physics would predict that all information about the matter is lost forever. However, quantum mechanics insists that information cannot be destroyed. This apparent contradiction gave rise to the black hole information paradox, which became one of the most profound puzzles in modern physics. Jacob Bekenstein and Stephen Hawking provided a key insight in the 1970s when they discovered that black holes possess entropy proportional not to their volume, as one might expect, but to the area of their event horizon. This finding implied that the amount of information a black hole can store depends on its surface, not its interior volume. From this emerged a revolutionary idea: the true degrees of freedom of a gravitational system are encoded on its boundary, not in its bulk. Building on these insights, Gerard T. Hooft and Leonard Susskind formulated the holographic principle in the 1990s as a general principle of quantum gravity. They proposed that the maximum amount of information that can exist within a region of space is proportional to the area of its boundary, measured in Planck units, rather than the volume of the region. This limit, known as the Bekenstein bound, implies that space is not an infinite reservoir for information. Instead, it behaves more like a finite storage system, where every bit of information corresponds to a tiny patch of the bounding surface. This notion stands in sharp contrast to classical intuition, where a larger volume suggests the capacity to contain more detail. If the holographic principle is correct, the universe fundamentally operates on rules very different from those suggested by our everyday experience. The holographic principle found its most precise formulation in the ADS/CFT correspondence, introduced by Juan Meldacena in 1997. This conjecture, which remains one of the most significant breakthroughs in theoretical physics in recent decades, posits a duality between two seemingly different theories: a gravity theory and a bulk de Sitter, ADS, space, and a conformal field theory, CFT, without gravity living on its boundary. According to this duality, every phenomenon in the bulk, including black holes and spacetime geometry, corresponds to a quantum field theory living on the lower dimensional boundary. This remarkable equivalence provides a concrete realization of the holographic principle, suggesting that gravity and spacetime itself are emergent phenomena arising from quantum degrees of freedom on a boundary surface. While our universe is not de Sitter in its large-scale geometry, the success of ADS/CFT in solving complex problems in quantum gravity and strongly coupled systems has made the holographic principle a central idea in modern theoretical research. The implications of the holographic principle are profound and far-reaching. If correct, it means that spacetime and gravity are not fundamental ingredients of reality but emergent phenomena, arising from more basic quantum information theoretic structures. It hints at a universe where the true description is not in terms of continuous fields and particles filling a volume, but in terms of discrete information stored on a lower dimensional surface. This perspective aligns with the growing recognition that information plays a foundational role in physics, leading to the view that the universe may be, at its most fundamental level, a vast information processing system. Despite its elegance and theoretical appeal, the holographic principle remains controversial because direct experimental evidence for it is lacking. Most of the evidence supporting it comes from theoretical consistency and mathematical success, particularly in the context of string theory and black hole thermodynamics. Some physicists have speculated about possible observational signatures, such as tiny correlations in the cosmic microwave background or noise patterns in gravitational wave detectors that might reflect holographic fluctuations, but these ideas remain speculative. The challenge lies in translating a concept that originated in exotic, high-energy theoretical frameworks into predictions testable in our observable universe. Critics argue that while the holographic principle is compelling within the context of ADS/CFT, its applicability to our universe, which appears to have a positive cosmological constant and an accelerating expansion, remains uncertain. Furthermore, the principle, as currently understood, does not yet offer a complete description of all physical phenomena. Supporters counter that even if its realization in our cosmos is not fully understood, the holographic principle likely captures a deep truth about quantum gravity and the nature of spacetime. Beyond the technical debates, the holographic principle invites profound philosophical reflection. If the three-dimensional world we experience is a projection of more fundamental information on a distant boundary, then our sense of reality is radically different from what intuition suggests. This idea echoes themes from ancient philosophy and modern speculation, from Plato's cave to the simulation hypothesis, where what we perceive as reality is not the ultimate layer of existence but an emergent phenomenon. Whether the universe is truly holographic remains an open question, but contemplating the principle forces us to confront the possibility that reality is fundamentally an information-based structure rather than a material one. Panpsychism. Panpsychism is one of the most fascinating and controversial ideas in philosophy and science because it challenges the standard assumption that consciousness is a rare, emergent property of highly complex brains. Instead, it proposes that consciousness, in some form, is a fundamental and ubiquitous feature of reality, present not only in humans and animals but also, to varying degrees, in plants, cells, molecules, and even fundamental particles. In this view, mind is not an accidental latecomer in a universe otherwise made of mindless matter, but rather a pervasive and intrinsic aspect of existence. This theory blurs the line between the mental and the physical, forcing a radical rethinking of both the nature of consciousness and the structure of the physical world. The roots of panpsychism stretch back to ancient philosophy. Pre-Socratic thinkers like Thales speculated that everything is full of gods, hinting at the idea that matter itself might be suffused with life or spirit. Later, thinkers like Giordano Bruno and Baruch Spinoza advanced visions of a cosmos in which mind and matter were two aspects of the same underlying reality. In modern philosophy, panpsychism re-emerged in response to the so-called hard problem of consciousness, the question of how subjective experience could arise from purely physical processes in the brain. Traditional materialist accounts struggle to explain how electrochemical signals, however complex, could give rise to the redness of red, the taste of salt, or the pain of a headache. This explanatory gap has led some philosophers and scientists to reconsider panpsychism as a serious alternative. The central claim of panpsychism is that consciousness does not suddenly appear when matter reaches a certain level of complexity, as in the human brain, but instead exists in rudimentary forms throughout the universe. Electrons, quarks, or atoms may not possess anything like human awareness, but they could have proto-experiential properties, basic building blocks of consciousness that, when combined in complex systems, produce the richer forms of experience we associate with animals and humans. Just as matter has both mass and charge at the most fundamental level, it may also have an intrinsic mental aspect. In this sense, panpsychism is not mystical but naturalistic. It treats consciousness as a real and irreducible feature of the physical world, alongside space, time, and energy. One of the strongest motivations for panpsychism is its ability to avoid the hard problem by refusing to treat consciousness as something that must emerge from non-conscious matter. If experience is built into the fabric of reality, then the mystery is less about how consciousness appears out of nowhere and more about how simple forms of experience combine into complex ones. This leads to what is known as the combination problem. If particles or atoms have tiny fragments of consciousness, how do these micro-experiences integrate into the unified, coherent consciousness of a human being? This remains one of the central challenges for panpsychism and a major point of criticism from skeptics. Despite this, the theory has gained traction in recent years, especially as neuroscientific and computational models of the brain have failed to provide a complete account of subjective experience. Thinkers such as Galen Strawson, David Chalmers, and Philip Goff have argued that panpsychism deserves serious consideration, not as a mystical notion but as a scientifically compatible worldview. Some interpretations suggest that panpsychism dovetails with modern physics, particularly quantum mechanics. In a universe where particles exist in superpositions and display non-local correlations, the idea that they may also have an inner, experiential aspect does not seem entirely implausible. Moreover, panpsychism resonates with certain interpretations of information theory and integrated information theory, IIT, which posits that consciousness corresponds to the integration of information in a system. If information and integration exist at all scales, then consciousness might as well. Critics, however, argue that panpsychism risks diluting the concept of consciousness to the point of triviality. If everything from electrons to boulders is conscious, then consciousness becomes so universal that it loses explanatory power. Skeptics also point out that there is no empirical evidence that simple physical entities have any form of awareness, and that panpsychism risks becoming unfalsifiable, a metaphysical stance rather than a scientific theory. Others argue that it does not actually solve the hard problem but merely shifts it. Instead of asking how consciousness arises from matter, we now have to ask how complex consciousness arises from simpler consciousness, which is not necessarily an easier question. Still, panpsychism carries profound philosophical implications. It challenges the reductionist view that the universe is ultimately composed of mindless matter, and instead invites a holistic perspective where the physical and mental are inseparable aspects of reality. It also has ethical consequences. If consciousness pervades nature, then perhaps our moral consideration should extend more widely, beyond sentient animals to all living beings, and in some interpretations, even to ecosystems or the Earth itself. While these ideas may seem radical, they echo intuitions found in many indigenous and Eastern philosophies, which see the world as alive and imbued with spirit. In sum, panpsychism is a controversial but increasingly influential theory that redefines consciousness not as a rare anomaly but as a fundamental property of existence. It avoids some of the pitfalls of materialism and dualism by positing that the mental and the physical are two sides of the same coin. Yet it faces the formidable challenge of explaining how microscopic consciousness combines into macroscopic awareness, and of providing testable predictions that distinguish it from other theories. Whether ultimately embraced, refined, or rejected, panpsychism pushes the boundaries of how we think about mind, matter, and the universe, and forces us to confront the possibility that consciousness is not the exception in nature, but the rule. Panspermia. The idea of panspermia belongs to that fascinating intersection between cosmology, biology, and philosophy, where questions about origins cannot be neatly contained within a single scientific field. At its heart, panspermia is the hypothesis that life on Earth did not arise entirely independently from inanimate matter here, but that its seeds, or at least the raw biological ingredients, came from elsewhere in the cosmos. The term itself derives from the Greek pan, all, and sperma, seed, literally, seeds everywhere. While often invoked in popular imagination as the notion of life raining down from the stars, in scientific discourse it is a more nuanced proposal about the distribution of organic material, microbial life, or prebiotic chemistry across planetary systems and even galaxies. The central motivation for panspermia is the puzzle of abiogenesis, how life arose from non-life. On Earth, the transition from chemistry to biology occurred very early in the planet's history. Evidence from isotopic ratios, microfossils, and stromatolite-like structures suggest that microbial life already existed by 3.5 to 3.8 billion years ago, perhaps only a few 100 million years after Earth cooled enough to maintain stable oceans. This rapidity raises a question: was the origin of life an almost inevitable chemical process that unfolds quickly wherever conditions permit, or did Earth benefit from a head start through seeding by preformed biological or prebiotic material from outside? Panspermia explores the latter option. There are several versions of panspermia, ranging from the modest to the more radical. Lithopanspermia suggests that microbial life could be transferred between planets within a solar system via rocks ejected by large impacts. When an asteroid strikes a planet with enough force, fragments of crust can be blasted into space. If microorganisms inhabit those rocks, some fraction might survive the acceleration, the vacuum, and radiation of space, and eventual re-entry and impact on another planet. We know that meteorites from Mars exist on Earth, so such interplanetary transport is physically possible. Laboratory studies have shown that certain hardy microbes, spores, and extremophiles can survive prolonged desiccation, high radiation, and shock pressures consistent with ejection and impact. This makes the idea at least biologically conceivable, though whether viable organisms could endure the millions of years such a journey might take remains debated. A broader version is interstellar panspermia, where material is exchanged not just within a planetary system but across stars. Here the challenges multiply: the timescales are far longer, radiation exposure is harsher, and the probability of capture by another habitable planet is vanishingly small. Still, advocates argue that given the sheer number of stars and the vastness of cosmic time, even rare events could occur. In this category one finds the idea that life's building blocks, such as amino acids, nucleobases, and sugars, may form in interstellar molecular clouds, on icy grains, or in comets, and then be delivered to young planets during their heavy bombardment phases. This soft panspermia does not insist that whole organisms travel, but that complex organic chemistry is widely distributed and can kickstart abiogenesis more readily when deposited in hospitable environments. An even more speculative extension is directed panspermia, proposed most famously by Francis Crick, co-discoverer of DNA's structure, and Leslie Orville. They suggested that life might have been deliberately seeded on Earth by an advanced extraterrestrial civilization, perhaps by launching spores or engineered microorganisms across space. While this shifts the problem of life's ultimate origin elsewhere, it highlights an important philosophical point. The question is not merely where life arose but whether the universe is generative of life in many places or whether our biosphere owes its existence to a singular, improbable event. Evidence invoked in support of panspermia is circumstantial but intriguing. Organic molecules are indeed abundant in space: amino acids, polycyclic aromatic hydrocarbons, sugars, and even precursors of nucleobases have been detected in meteorites, comets, and interstellar clouds. The famous Murchison meteorite, which fell in Australia in 1969, contained over 70 different amino acids, many not found naturally on Earth. Space missions such as Rosetta's study of Comet 67P/Churyumov-Gerasimenko have confirmed that comets carry complex organic molecules. These findings demonstrate that prebiotic chemistry is not unique to Earth and that the ingredients of life are widespread. Yet, having ingredients is not the same as having organisms, and so the evidence remains suggestive rather than decisive. Critics of panspermia argue that it does not solve the fundamental question of life's origin but merely relocates it. If life began elsewhere, how did it arise there? At some level, abiogenesis must have occurred, whether on Earth or beyond. Moreover, while the physics of rock transfer between nearby planets is plausible, the biology of long-term survival through cosmic radiation, DNA damage, and long dormancy is highly uncertain. Most microbes tested so far can endure harsh conditions for years or decades, but interplanetary travel may take millions of years. Some extreme organisms, such as Deinococcus radiodurans or certain bacterial spores, exhibit extraordinary resistance, leading advocates to suggest that survival is at least not impossible. However, survival is not binary. Even if a fraction of organisms persist, their metabolic dormancy, DNA repair limits, and recovery after re-entry remain significant hurdles. Another contentious point is the interpretation of supposed microfossils in meteorites. Claims in the 1960s and more famously in the 1996 announcement about the Martian meteorite ALH-84001 suggested possible microbe-like structures preserved in extraterrestrial rock. Later studies questioned whether these features could be produced by abiotic processes, and no consensus has emerged that they represent life. The controversy reflects both the tantalizing possibility that extraterrestrial life might have left traces and the caution required to avoid false positives. Philosophically, panspermia challenges traditional narratives about life's uniqueness. If life is seeded across the cosmos, it might mean that biology is a cosmic phenomenon rather than a local accident. It could imply that every habitable niche is predisposed to become inhabited, not because of convergent abiogenesis, but because life spreads like spores across time and space. On the other hand, even if panspermia occurred in our history, it does not guarantee that life is common. It could be that Earth is one of few recipients of such seeds in an otherwise sterile cosmos. Modern research continues to probe the plausibility of panspermia through experiments on microbial survival in space. The International Space Station has hosted long-duration experiments exposing microbes and spores to space conditions, and some have survived years of exposure. Astrobiologists also study the shielding properties of rock fragments and ice, the protective effects of dust or regolith, and the chemical evolution of organics under UV radiation. Missions that analyze comets, asteroids, and planetary atmospheres extend this inquiry. In the coming decades, exploration of Mars, Europa, Enceladus, and Titan may reveal whether independent biospheres exist, or whether signs point to shared ancestry, which would be striking evidence for panspermia. In the scientific mainstream, panspermia remains controversial, partly because it can feel like a displacement hypothesis rather than a resolution of abiogenesis. Still, its modest versions, particularly lithopanspermia within a planetary system, are widely regarded as physically plausible. Its stronger versions, interstellar seeding or directed panspermia, veer toward speculation but stimulate valuable discussion about the resilience of life and its cosmic context. At its most profound, panspermia is not just a claim about history but an invitation to reconceive biology as part of a larger cosmic process, challenging us to ask whether life is an earthbound phenomenon or a universal tendency of matter in motion. String theory. String theory is an ambitious theoretical framework that attempts to unify all known forces of nature, including gravity, into a single, coherent description. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles, as described in the standard model of particle physics, but instead tiny, one-dimensional strings that vibrate at specific frequencies. These strings are unimaginably small, on the order of the Planck length, about 10 to the 35 th power meters, far beyond the reach of current experimental technology. The vibrational modes of these strings determine the properties of the particles we observe, such as mass, charge, and spin. In this way, the rich variety of particles in nature, quarks, electrons, photons, and even hypothetical gravitons, emerges not from different types of fundamental matter, but from different patterns of string vibration, much like different musical notes produced by the same violin string. One of the motivations for string theory is the long-standing challenge of reconciling general relativity, which describes gravity and the large-scale structure of the cosmos, with quantum mechanics, which governs the behavior of particles at the smallest scales. Attempts to quantize gravity using traditional methods lead to infinities that cannot be removed, making a consistent theory impossible. String theory, however, smooths out these infinities because strings, being extended objects, do not concentrate interactions at single points as particles do. This elegant feature allows string theory to incorporate gravity naturally, predicting the existence of a massless spin, two-particle, the graviton, that mediates gravitational interactions. For this reason, string theory is often considered the most promising candidate for a theory of everything, uniting quantum mechanics with general relativity. A striking implication of string theory is that it requires additional spatial dimensions beyond the familiar three. In its simplest versions, the theory demands 10 dimensions of spacetime, 9 of space and 1 of time. More advanced formulations, such as M-theory, which emerged in the 1990s as a unifying framework for different string theories, suggest 11 dimensions. These extra dimensions are not directly observable because they are thought to be compactified, curled up so tightly at extremely small scales that they remain hidden from view. The geometry of these compactified dimensions, described by complex shapes known as Calabi-Yau manifolds, plays a crucial role in determining the physical properties of our universe. Different ways of compactifying these dimensions could give rise to different laws of physics, potentially explaining why our universe has the specific properties it does. String theory also introduces a new type of object called a brane, short for membrane, which can exist in multiple dimensions. Strings may be open, with free ends attached to branes, or closed, forming loops. Our entire observable universe might reside on a three-dimensional brane embedded in a higher dimensional space, while gravity, carried by closed strings, can move between branes, providing a possible explanation for why gravity appears so much weaker than the other fundamental forces. This idea has inspired scenarios in which multiple branes exist, sometimes colliding, giving rise to cosmological models in which the Big Bang was triggered by a brane collision. Another profound feature of string theory is its mathematical richness. The theory incorporates advanced concepts from geometry, topology, and quantum field theory, revealing deep connections between areas of mathematics and physics that were once thought unrelated. Dualities, relationships showing that seemingly different theories describe the same underlying physics, have provided insights into black holes, quantum gravity, and strongly coupled systems. These mathematical structures have led to practical tools, such as the ADS/CFT correspondence, a conjectured duality between a gravitational theory in a higher dimensional space and a quantum field theory on its boundary. This correspondence has become a powerful tool for studying quantum systems, even beyond string theory itself. Despite its elegance and potential, string theory remains controversial because it lacks direct experimental evidence. The energy scales at which string effects become apparent are so high, near the Planck scale, that no current or foreseeable particle accelerator can test them. As a result, string theory exists largely in the realm of theoretical physics, supported by mathematical consistency rather than empirical confirmation. Critics argue that its vast flexibility, including the enormous number of possible solutions known as the string landscape, estimated at around 10 to the power of 500 different vacua, undermines its predictive power. This abundance of possibilities means that string theory can accommodate almost any observed physical reality, leading some to question whether it qualifies as a scientific theory in the traditional sense. Proponents counter that this richness reflects the true complexity of the universe and that indirect evidence, such as signatures in cosmology or black hole physics, might eventually favor string theory over other approaches. The string landscape has also inspired discussions of the Anthropic Principle and the multiverse. If string theory allows for an immense number of possible universes with different laws of physics, then our universe might be one of many, selected for its compatibility with life. This idea has generated philosophical debate as well as criticism for moving away from the traditional goal of making unique, testable predictions. Nevertheless, string theory continues to drive progress in theoretical physics, offering insights into quantum gravity, the early universe, and even condensed matter systems. Ultimately, string theory is as much a framework as it is a specific theory, providing a conceptual foundation for exploring the unification of nature's forces and the fundamental structure of reality. While it may take decades, or perhaps centuries, before its validity can be confirmed or refuted, its influence on physics and mathematics is undeniable. It challenges our intuition, expands our understanding of space, time, and matter, and suggests that the universe may be far more intricate and interconnected than our current observations reveal. Technological singularity. The technological singularity is a controversial concept that envisions a point in the future when artificial intelligence surpasses human intelligence so dramatically that it triggers an exponential acceleration of technological progress, producing transformations that are unpredictable, uncontrollable, and possibly irreversible. At its core, the singularity is not merely about the invention of smarter machines, but about a radical shift in the trajectory of human civilization, where technology ceases to be a tool we control and becomes an autonomous driver of evolution, reshaping society, economy, and even the nature of humanity itself. The idea has roots in the mid-20th century, when early computer scientists and mathematicians such as John von Neumann and I.J. Good speculated about the potential of ultra-intelligent machines. Good famously argued that the first ultra-intelligent machine could design even better machines, setting off a recursive cycle of self-improvement that would quickly leave human intelligence far behind. This runaway process, in theory, would lead to a qualitative break in history, a singularity, borrowing a term from physics to describe a point beyond which the known laws no longer apply. In the 1990s and 2000s, futurists like Werner Ving and Ray Kurzweil popularized the concept, framing it as an inevitable outcome of exponential trends in computing power, particularly Moore's law, which describes the doubling of transistors on microchips approximately every 2 years. Kurzweil argued that such exponential growth will eventually culminate in machines that not only match human cognition but rapidly exceed it, leading to unimaginable advances in medicine, science, and society. At the heart of the singularity lies the idea of artificial general intelligence, AGI, a level of machine intelligence that can perform any intellectual task a human can. Unlike today's narrow AI systems, which excel in specific domains such as language processing or image recognition, AGI would possess flexible reasoning, creativity, self-improvement, and adaptability across tasks. Once such an AGI is created, proponents argue, it could redesign its own software and hardware in a process known as recursive self-improvement. Each new generation of AI would be smarter than the last, accelerating progress until human cognitive capacities are dwarfed. This cascade could occur far faster than human evolution or even human cultural adaptation, producing what amounts to an intelligence explosion. The potential outcomes of such an explosion are deeply divisive. Optimists see the singularity as a gateway to extraordinary progress. Superintelligent AI could cure diseases, solve climate change, eliminate scarcity through advanced automation, and even enable radical life extension through biotechnology and nanotechnology. In this vision, humanity merges with machines, enhancing itself through brain-computer interfaces and genetic engineering, achieving a form of post-human existence that transcends biological limitations. The singularity, from this perspective, is not an end but the beginning of a new era of abundance and possibility. Skeptics and critics, however, warn that the singularity could be catastrophic. A superintelligent AI might pursue goals misaligned with human values, and because it would operate at speeds and scales incomprehensible to us, we might lose the ability to control it. Even without malicious intent, Such an AI could cause existential harm by single-mindedly optimizing for objectives that conflict with human well-being, an idea sometimes illustrated by thought experiments like the paperclip maximizer, in which a superintelligent machine tasked with making paperclips converts the entire planet into paperclip factories. Critics argue that once an AI reaches a certain threshold of autonomy, containing or controlling it could be impossible. This possibility raises urgent questions about AI alignment, safety research, and governance. Controversy also surrounds the very plausibility of the singularity. Some scientists argue that exponential trends in computing cannot continue indefinitely, as physical limits such as energy consumption, heat dissipation, and quantum effects will impose constraints. Others contend that intelligence is not merely computational speed or data processing but involves embodied, social, and emotional dimensions that may not be replicable in machines. From this perspective, human consciousness is not simply the output of algorithms but a product of biology, making the leap to machine superintelligence far less certain than singularity advocates suggest. Beyond technical feasibility, there are cultural and philosophical critiques. Some see the singularity as a modern myth, a form of techno-utopianism that reflects humanity's perennial yearning for transcendence, echoing religious visions of apocalypse and salvation. In this sense, the singularity may function more as a cultural narrative than a scientific prediction, a story about humanity's fear of obsolescence and its hope for immortality through technology. Others see it as a distraction from more pressing and immediate issues, such as the economic disruption caused by automation, the ethical challenges of biased AI systems, and the geopolitical risks of AI arms races. Despite skepticism, the singularity continues to capture public imagination because it touches on fundamental questions about what it means to be human in an age of accelerating technology. If machines surpass human intelligence, will we still be the authors of our destiny, or will we cede control to entities beyond our comprehension? Will the singularity represent humanity's greatest triumph, achieving mastery over nature and transcending mortality, or its ultimate downfall, as we unleash forces we cannot contain? In summary, the technological singularity is a controversial and speculative theory that envisions a future where artificial intelligence rapidly outpaces human intelligence, leading to unpredictable and possibly irreversible transformations. It is celebrated by some as the dawn of a post-human future and feared by others as an existential threat. Whether it represents a realistic outcome of technological progress or a cultural myth reflecting our hopes and anxieties, the singularity forces us to confront the trajectory of innovation and the profound implications of creating minds that could surpass our own. Emergent gravity. Emergent gravity is the idea that gravity is not a fundamental interaction on the same footing as the electromagnetic, weak, and strong forces, but rather a macroscopic, collective phenomenon that arises from more microscopic degrees of freedom, much as temperature, pressure, or elasticity emerge from molecules. In this view, spacetime geometry and the gravitational field equations are effective, large-scale descriptions of underlying quantum constituents whose precise identity is not yet known. The appeal of this perspective is twofold. First, the known laws of gravity display striking thermodynamic and information-theoretic fingerprints. Second, emergence provides a template for reconciling gravity with quantum mechanics without quantizing geometry in the usual way. The modern thread begins with black hole thermodynamics. Black holes obey analogs of the ordinary thermodynamic laws. They have an entropy proportional to the area of the event horizon and a temperature set by surface gravity. That entropy-area relation is extraordinary. It suggests the fundamental information content of a region scales with its boundary rather than its volume. If horizons carry entropy and temperature like ordinary systems, it is natural to ask whether gravitational dynamics themselves are equations of state. Ted Jacobson made this logic precise by assuming that every spacetime point admits a small causal horizon with Unruh temperature and Bekenstein-Hawking entropy proportional to area. Imposing the Clausius relation, heat flow equals temperature times entropy change, on all those local horizons yields Einstein's field equations. In that derivation, curvature is not fundamental, it is the thermodynamic response of the system to energy flux. Gravity, then, looks like hydrodynamics. The Navier-Stokes equations are not fundamental laws of water but universal, coarse-grained statements about many molecules. Einstein's equations may be the universal, coarse-grained statement about many microscopic, gravitational atoms. A second strand recasts gravitational attraction as entropic. Eric Verland showed that if information about matter is stored on holographic screens and if entropy changes with the position of a test mass, then the entropic tendency to maximize disorder yields a force with the form of Newton's law. In that picture, a particle approaching a screen increases the number of accessible microstates. The resulting entropy gradient creates an effective force we interpret as gravity. Extending the idea, Verland later proposed that the observed mass discrepancies in galaxies, usually attributed to dark matter, could arise from an elastic, entropic response of spacetime to the entropy associated with dark energy at cosmological scales. In this account, inertia and the extra pull in galactic rotation curves are emergent, not evidence of unseen particles. While this framework captures some galaxy-scale phenomenology reminiscent of MOND, it faces challenges at the scales of galaxy clusters, gravitational lensing maps, and the cosmic microwave background, where the particle dark matter paradigm remains remarkably successful. Entropic gravity, therefore, is best regarded as a provocative heuristic pointing at deep statistical structure, not a finished replacement for standard cosmology. A third and arguably deeper route to emergence comes from holography. The holographic principle asserts that the full physics of a volume can be encoded on its boundary. In AD/CFT duality, a quantum field theory without gravity living on a boundary exactly captures a bulk spacetime with gravity. Bulk geometry and even black holes are re-expressions of boundary quantum states. This duality makes spacetime from entanglement concrete. The entanglement entropy of a region in the boundary theory computes the area of a minimal bulk surface. Patterns of quantum entanglement stitch together the bulk's geometry, and changing those patterns literally changes curvature. From this vantage, gravity is the hydrodynamics of entanglement. Linearized Einstein equations emerge from entanglement first laws. Bulk locality is an approximation encoded by quantum error-correcting codes. And wormholes relate to entanglement, ER equals EPR, rather than spatial tunnels carved into a pre-existing manifold. Although our universe is not anti-de Sitter, these results offer a proof of principle. With the right microscopic quantum system, spacetime and gravitational dynamics appear as emergent, large-scale phenomena. There are further, complementary hints. In the membrane paradigm and fluid gravity correspondence, the near-horizon dynamics of black holes map to viscous fluids obeying Navier-Stokes-like equations, complete with a universal ratio of shear viscosity to entropy density in certain regimes. In induced gravity, a la Sakharov, quantum fluctuations of matter fields living on a background endow it with an effective elastic action. Newton's constant and the Einstein-Hilbert term appear as radiative corrections, as though spacetime were a medium whose stiffness derives from microscopic quantum constituents. Even analog models in condensed matter, superfluids, Bose-Einstein condensates, and emergent gauge fields, show how relativistic excitations and effective geometries can arise from very non-relativistic substrates, reinforcing the plausibility, though not the details, of gravitational emergence. Because emergent gravity is an umbrella rather than a single theory, its proposals differ in their ambitions and their vulnerabilities. Thermodynamic derivations elegantly explain why area, temperature, and entropy are woven into gravitational law, but they do not identify the microstates of our universe or predict their spectra. Holographic duality supplies a complete microscopic account, but chiefly for negatively curved spacetimes and special quantum field theories. Extending those lessons to accelerating, de Sitter-like universes remains an open frontier. Entropic and elastic models aim at galaxy dynamics without particle dark matter, yet must reproduce, with comparable precision, cluster lensing, structure formation history, and the acoustic peaks of the microwave background. Induced gravity ideas naturally generate Einstein's action but must control divergences and explain the observed smallness and sign of the cosmological constant. Any fully convincing emergent account must also secure cherished empirical pillars, the equivalence principle to exquisite accuracy, local Lorentz invariance, causal structure, and the detailed weak field tests and gravitational wave signals already verified. The conceptual payoffs, however, would be profound. If gravity is an equation of state, then quantizing that equation directly, as one quantizes sound waves rather than atoms, may miss the point. The true quantum theory lives in the microscopic degrees of freedom whose collective variables we call metric and connection. If geometry is a manifestation of entanglement, then space is literally the bookkeeping of quantum information, and time evolution is coarse-grained dynamics of entanglement patterns. If inertial and gravitational effects are entropic responses, then the arrow of time and the growth of spacetime volume may be inseparable from the second law. In all these pictures, gravity's universality, geometric form, and thermodynamic flavor cease to be mysteries and become necessary features of the large-scale limit of a deeper quantum many-body system. The outstanding questions are clear. What are the microscopic constituents that give rise to our nearly de Sitter cosmos? How, precisely, do local quantum field theories of matter and gauge forces co-emerge with geometry while preserving the equivalence principle? Can one derive, not assume, the observed value of the cosmological constant, the detailed power spectrum of primordial fluctuations, and the late-time cosmic acceleration? Where, if anywhere, do new, falsifiable signatures appear that distinguish emergence from the particle dark matter paradigm or from quantized geometry approaches? Until such questions are answered, emergent gravity remains a compelling research program rather than a settled theory, a disciplined bet that the curvature we measure is to some as yet unknown microphysics what pressure is to molecules, real, predictive, and universal, but not fundamental.